to operate with the shortage of labor. We need to operate with less professionals and use the technology too. So you're not going to be in any shortage of technological, challenges for you. So this is what I wanted to share a little bit with you. When you hear about mining, whether it's gold, whether it's copper, don't look at it as for what it used to be. Look at it of what it provides. And look at it as our responsibility and shared responsibility in doing this. And if we want a North American strategy, be aware that 80% of those elements are on indigenous land. So only partnership, only working together, everything that you're doing this week at the bigger scale will have to happen. On this, I wish you all the best. You're awesome. I had the chance to interact with some of you this morning. Wow, we're far from the little bazooka that we used to build on the street, right? But we did reach 200 feet with those little bazooka back in the day, so I know you're going to do much better. So be responsible as you enter the industry, and start being those leaders of tomorrow. Always remember that everything starts with the interactions with Mother Earth. And we need to do it in a more responsible way as we advance in time. On that, all the best, wish you the best. Be safe out there, be good in everything you do, but more importantly, be kind to each other. Thank you, have a great day.
Okay, thank you so much, Mr. Adams, for telling our students about these exciting opportunities coming up in the mining industry, particularly for designers and engineers, and also about the way that the mining industry works collaboratively with local communities. So let's have one more big round of applause to I Am Gold for the fabulous breakfast. Okay. We now have a number of presentations from student teams, but before we begin, I would like to invite our conference director, Ariana Kresniak, to the stage to tell us about the first ever Launch Canada conference raffle. Here she comes.
Hello, everyone. Thank you very much for being here today. I hope you are enjoying your breakfasts. So, we have a full roster of talks today from you, the student teams. We're starting with See You in Space. We're hearing from Arbalest, UVic, U Waterloo, Toronto. We've got a full lineup. Every talk that you attend, I'm going to go through the aisles and give you a raffle ticket. You should have all, with your breakfast, gotten a raffle ticket. If you present, we'll give you 2 raffle tickets to say thank you. At the end of the day, around 3:45, I will draw raffles. The prizes are a Lego Artemis set, a full model kit that'll fly to 700 feet with 2 motors for it, a flight of hot sauce from a local Timmins business that flew the seeds up to 50 kilometers on a weather balloon to expose it to radiation and make the hot sauce hotter. It's 1.5 million Scovilles. And gift cards to local Timmins restaurants so you can stay fed while you're here. So that will be drawn at about 3:45. You have to be here to get the ticket. If you're drawn and you're not here, I'm moving on to the next person. So if you have to leave, give your tickets to a trusted team member so that they can win on your behalf. Thank you very much and have a great day.
Thank you so much, Ariana. I so want that hot sauce. And I'm at every presentation, so. Okay, our first student presentation of the day is by Anuj Snyder from Carleton University See You in Space. Anuj is the team's recovery lead, and he's going to tell us about the team's updated skirt reefing recovery system developed for their hybrid competition rocket, Iced Capogee. I love that name. Just a reminder, if you have questions for any of the speakers after their talk, come up and use the two mics on either side. That would be hugely appreciated. Okay, Anuj, are you ready to go? There you are.
Okay, quite a few of you. Alrighty, so hello everyone. My name is Anuj, and thank you for the introduction. I'm the recovery lead on CU in Space, and today I'm going to be presenting, along with my colleague Michaela, about our skirt reefing recovery system for LC 2026 competition rocket, Iced Capogee. So, before we get started, we'll do a little agenda. We're going to cover 4 things today. We're going to cover an overview of reefing in itself and our reefing system and the design goals we set out to accomplish. We're also going to cover the wireless communication electronics for reefing and how that worked. And we're also going to cover our new toroidal parachute design that helped us save a lot of space in our rocket this year. Finally, we're going to talk about future design steps and what we learned through these past 2 years of our reefing system. So just wanted to do a bit of a flight overview for CR26H. So as previously stated, we have a hybrid rocket, but today I'm going to be focusing on steps F and G there, which is our recovery. So we accomplished this through reefing, which means we only have a single split, and we have 2 deployment events, where our parachute comes out reefed, and then at our main deployment apogee, 1,500 feet, we disreef our parachute by cutting our reefing line. So let's talk a bit about our initial design goals. Our biggest one this year was we wanted to reduce our total recovery volume. Last year on our competition rocket, quarter pounder, we had a very large recovery volume, as we'll get into a bit later, and we had a very large oversized chute. And so we wanted to make an effort to make our system more efficient and reduce that total recovery volume. We also wanted to make arming easier. Last year, as with this year, we're using screw switches to arm. And without any sort of guide, it's very difficult to see them in the rocket, especially on a very tall rocket when you're up on the top step of a ladder. We also really wanted to reduce integration time and effort on the pad itself. And as you can see through those 2 images, there was a lot of that last year. We assembled the whole recovery system on the pad, which was pretty inefficient and very, very stressful. So let's talk about recovery in quarter pounder. This was last year's LC competition rocket. And as you can see there, that whole center section was our recovery system. This rocket was over 15 feet in length at a 6-inch diameter. And recovery was over 1 meter of body tube space. So we had a very large 4-meter diameter chute. And it was very space inefficient. We also didn't have a seal on our bulkhead, so we were using a separate plate to seal it. So that the system worked in other rockets, but it just wasn't very efficient. So we wanted to make it better. So let's talk a bit about recovery in CR26H Iced Capogee. So as you can see there, that purple box with the parachute bay label is the entire recovery system for CR26H. It's only 600 millimeters long, so over 40% smaller when compared to quarter pounder, our previous rocket. 17% of the rocket's length in comparison to over a quarter from last year. So we've gotten a lot more efficient, and let's talk a bit about how we did that. So I want to cover a bit about what reefing is for anyone who doesn't know. Essentially, it's a method of parachute deployment and recovery where you only need a single split. So typical rockets will have a dual split, dual deploy method, where you deploy your drogue at apogee, and then deploy another main chute, split the rocket again for your main parachute. Reefing accomplishes this by combining two chutes into one. So you have a drogue parachute that's constricted in its diameter, and then you disreef it through various methods. Ours is skirt reefing, and that means we tie a line around the skirt and we cut that line at 1,500 feet, our main deployment apogee, or altitude. So let's do a bit of a general reefing system overview. So as you can see through this bit of a flow chart, we have our stowed composition on our left with our deployment electronics and energetics attached to our avionics stack, and that's above our recovery bulkhead, so that's above the seal. We have wire pass-throughs for our deployment through the bulkhead, and then we have our recovery electronics and our parachute stowed in that body tube. When the parachute comes out in its reefed configuration, we have 24 reefing rings around our toroidal chute that hold in the reefing line and constrict the diameter of the chute, allowing it to fall at proper drogue speeds. And then finally, at our disreefing altitude, we cut that line and allow the chute to unfurl to its full diameter. So this is a bit more in depth into exactly what's on LC 2026. And you can see from that graphic on the right kind of how our system goes together. So we have the recovery bulkhead with the avionics stack on the left side of it. We also have our transmitting box, which transmits our wireless reefing signal to our receiving boxes, which are on the parachute. So we attach those to the parachute through little quick links, and they receive that wireless signal, telling them to cut the line at 1,500 feet. We also have SRAD deployment energetics, our black powder charge cannons, that facilitate our split at our apogee. So let's talk a bit about our reefing system. So the receiving boxes, as I mentioned, they receive the disreefing signal from our transmitting box, and they cut that reefing line. And they're located on either side of the skirt of the parachute, as I said, attached through quick links. As you can see, they contain a battery, a Pico PCB, and for redundancy, our other receiving box contains a Easy Mini altimeter, which also facilitates cutting the line. They also contain a screw switch with a mount, which is how we solved our arming issue. We created these 3D printed mounts that attach to our screw switch, and they allow basically guiding into the screw switch hole. It also has, obviously, the Mako line cutter. So the transmitting garage door, as we like to call it, it's a transmitting box that receives the wired disreefing signal from our avionics stack altimeter. So we have an Easy Mini that facilitates our apogee deployment. That sends a wired signal at 1,500 feet to this transmitting box that then sends the wireless signal up to our SRAD Pico PCB in our receiving box, and that cuts our line. This remains attached to the bulkhead throughout the whole flight through 3D printed spacers. And so this one's pretty self-explanatory, just a PCB, a screw switch, and then an arming hole. So now I'm going to invite Michaela up to talk a little bit about the hardware and software of our PCBs in our reefing system.
Thank you, Noosh. My name is Michaela, and I worked on the software and the hardware systems of our reefing system. So as you can see here, we have our PCBs. This is the board that is connected to our Pico. So we have two Picos on the reefing. We refer to them as a server, which is actually on the rocket, and the client, which is on the parachute. So the PCB is connected to both of these. Its job is to amplify the signal from the Pico and send it to the correct place on our rocket. So the first place it connects is the altimeter. This is connected to our avionics stack on our rocket. So when it reaches 1,500 feet, when our parachute is supposed to reef properly, it will send a signal to our picos telling it it's time to tell the parachute to reef, and hopefully our rocket comes down in one piece. Then we have our eMatch terminal. So this is going to be connected on the client side. This is connected to our reefing cutter. So when the client receives the signal from the server pico, it will send a signal to the Mako cutters, and it will cut the reefing line, and our parachute will properly inflate. We also decided this year to add a bigger buzzer. Last year we encountered a problem that we couldn't hear when the picos were armed on the actual launch pad because it is quite loud out there. We decided to create a buzzer that was louder and that could also handle more sounds, so we're able to tell when everything is armed properly. So, now getting into the more software side of our picos, we decided to make the change this year from Python using Thonny to C using VS Code. We mostly did this because Python has a lot of pre-built functions for networking that aren't as efficient as C could be. We decided to build the system from the ground up, and this gave us the ability to handle errors easier and make it much more efficient. And anyone that works with C will know that it's also quite faster than Python could ever be. This also gave us the ability to create our own CSV data storage function. So this is our data retention system. When the server sends signals to the client, since it's a UDP function, which I'll get into in a second, it's going to be sending signals repeatedly, which can cause quite a lot of bloat if we are retaining all of that data. So what we did is we did an override feature that instead of saving 30 different state functions, we have it overriding, so we said send it a state function 4, 5, 6 times, depending how many times it happens. All right. So now I'll go a bit more into why we made the transition from TCP to UDP this year. So TCP signals are when the server and the client stay in communication the whole time. So when the server sends a signal to the client will send an acknowledgement back to the server, and then the server knows to send the next state. And it goes over and over again. We realized that we did not need this year because we only need one signal to get through from the server to the client in order to cut the reefing line. So, keeping in TCP, we'd have a lot of backlog. So we made the decision to translate over to UDP. And as you can see from this flowchart, this is how our UDP system works. So first, we arm both the server, which is seen in blue, and the client, which is yellow here. Then after we arm them, they connect to each other. So the server is going to send out signals like crazy, and the client, once it receives a connection, it will send back its IP address, and then the server knows where to send all of the signals. Then the server no longer receives anything from the client. It will just start sending states like crazy. Here we have, it will send state 1 and will repeatedly check to see if the altimeter has gone low, which means it needs to blow the reefing line. The client, it will repeatedly check if it needs to blow the reefing line. If yes, the server will start sending below the reefing line, and it will go into a loop until everything has gone through and the reefing line is blown at 1,500 feet. And now I'll hand it back off to Anush to talk a bit about parachute design.
Alrighty, hello. So we're going to talk a bit about our parachute design, which is probably the biggest improvement that we've had on our system this year. So we have a brand new toroidal parachute design, and essentially the main benefit of a toroidal parachute is that its coefficient of drag is much higher than your typical hemispherical, because the vent is pulled in to kind of create that donut shape. And so that allowed us to make our chute much smaller, along with reducing weight on the rocket. And so our disc reef diameter is only 2.3 meters, which means our chute can be compacted quite tightly. We made our chute out of ripstop nylon, and it also has a 10-foot shot cord from the vent to the skirt, which is pretty typical for toroidal chutes to allow that kind of pulling in of the vent and creating of that shape. It's a 12-gore parachute, and our dry rocket mass is only 29 kilograms. So with a coefficient of drag of 1.8, we could create this chute quite efficiently and save a lot of space in our system. So as you can see there, it's over 40% smaller than the chute that we used in LC 2025, which is how you can see how we saved so much space. And there's a little GIF there and a good image of it being inflated. And if you'd like more videos of the reefed inflation, come talk to me afterwards. So let's talk a bit about dimensions and modeling. So we have our own models that we use for our parachutes that were created graciously for us, and we've created on our own. We use the flange calculator, the flange method, to calculate our reefed area, diameter, and all of our forces. And then we also have several toroidal calculators that we use to create our gores, our individual gores, to create our own chutes. And then the 3D toroidal model of what our chute would look like. And then we hand sew it all by ourselves and install our reefing lines on, our reefing rings with ribbon. So let's talk a bit about what we learned, both from LC 2025 and so far testing this system for LC 2026. The main thing we learned is that you design to integrate, not necessarily to optimize. So when we were focusing on LC 2026, we focused mostly on how to get as small as possible, and less so on the actual integration, whether that be the night before or on the pad. And so that caused a bit of issues with us so far in our system this year, which we've since been able to fix. But really the lesson we've learned is that by designing to integrate easier, you are optimizing your rocket. By making an easier time on the pad, you are making a better rocket, even if it's not necessarily saving space or weight. We also learned to put our parachutes to the test, preferably as early as possible. So you really want to make sure that your parachute can inflate properly, the line cutters work properly, and it's much better to start testing earlier to know if you have to make any modifications to the chute. And we also learned that simpler is better. There's no need to overcomplicate things. Rockets are already, and parachute systems are very complicated systems, so the easier you can make them, the better. And that image there is just a bit of an aftermath from our LC 2025 sport flight rocket. And that was kind of our recovery system. As you can see, it's a thing. So a bit of our next steps, what we're looking forward to doing next year. So we're looking to decrease the receiving box size. The receiving boxes on the parachutes right now are pretty heavy, and they're quite large because we're restricted by the size of our Mako line cutters, which leads into that third point there, SRAD line cutters. So we're looking forward to creating a new kind of system, or taking inspiration off of a previous one, to create smaller line cutters, which will allow us to reduce the size of our boxes and thereby create a more efficient and hopefully easier to assemble system. We also want to simplify our deployment electronics. If it's possible to find a way to place them all on our parachute to do both our apogee and our drogue deployment, and our main deployment, that would be ideal for us, again, to reduce space and reduce complexity of our system. We found this year that with the system we've made, there's a lot of bits and bobs and small items that you need to properly make this system work, so we're hoping to reduce that as much as possible next year to make integration easier. Finally, we want to start gathering real experimental parachute data to create our own experimental models that we can base our parachute calculations off of. And so that's really important if you want to create accurate parachute models. Because manufacturing differences and small differences in your environment can have a big difference on how your parachute performs. So getting experimental parachute data to plug into those calculators is very important. And that's pretty much it. I hope you enjoyed and I hope you learned something. So thank you. Gets in there! Is there any questions? No, all good? All right.
Thank you so much to Anuj and Michaela and See You in Space for that excellent presentation and for sharing the lessons that you've learned along the way. We are looking forward to seeing your toroid floating down from the clouds, and best of luck with your recovery of iced Kappa-G. Our next presentation is by Arbalest Rocketry from York University. We have with us the two payload co-leads, Nathan Minnick and Syed Masumi Lari. It is my pleasure to invite them up to the stage. They're going to tell us about their dino-luminescent payload and their new method for exposing a biological luminescent payload to controlled light and capturing the results with in-flight imaging. Let's welcome Arbalest to the stage. Where is Nathan and Syed? Getting slides ready. Okay, one moment.
Hello everyone, welcome to our presentation. Today we will be talking about our payload this year, and it's a very unique one. We're very happy to show you what we've been accomplishing in the past year. So I want you guys just to pay attention to the video in the center here and observe the following cell. So what you're watching is a very unique algal cell. It's one of the largest cells known to the world and has a very unique property. It has no way of moving on its own. So the cell does not move at all in natural environments. Now watch. It just moved. So what we've been able to achieve in the previous year in Dr. Ozzy Mermut's lab was to actually move a cell which has no method of moving. And this is very unique because it's kind of like giving an organism that has no legs. So how were we able to do this? And why is this relevant for rocketry? Well, before we get there, we have to start at the beginning. These cells are very unique. So this cell is called Pyrocystis fusiformis. It's an algal dinoflagellate, and it has very unique optical properties. The cell actually glows blue in the dark when you shake it. And initially, this was of interest to us in the scientific world because it was a very cool environmental reporter. So what our lab was trying to do originally is to use a very special compound, PDPES, you see it mentioned here, to actually change the shape of these cells to induce that dark glowing pattern. And while we were trying to do these experiments, we found something very, very unexpected. That was not actually the goal of our experiments. And again, you've seen this already, but you can see here that again, we're moving a cell that has no way of moving on its own. And the way we're doing this is by combining that special compound that I talked about and ultraviolet radiation. Now, this should start to sound very familiar to a lot of you. So here, again, sorry about that. Just here, same video as before, depicted with just more exact movements. But this phenomenon should seem really, really familiar. By a raise of hands, how many know where this is from? Raise of hands. Yay, okay, good. We have a few in the audience. Yeah, so for those of you who have not watched the movie, in Project Hail Mary, there's a very special type of cell called an astrophage. And in this science fiction movie, the cells would move towards the light. And when the movie was released, this was essentially science fiction. Humanity had never discovered a cell that, without having any ability to move on its own, would move towards light. But 6 months ago, we discovered this phenomenon, and it's really, really cool. So why is this relevant to rocketry? Well, we know how to make this phenomenon work. We know how to get the cell to move, but we have no idea what's actually happening. And one of the ways that we can figure out what this phenomenon is actually underlying is to remove one force that's always present, even in this room, and that force is gravity. So if you recall, we're always applying this ultraviolet radiation onto the cells, and somehow this light is inducing a force that's moving these cells. But there's always gravity present. So by removing that force, we can actually discover what the property of just the movement caused by that LED light, that UV LED light is. And we're doing this using a rocket. But how are we actually accomplishing this? Well, that's for the engineers to tell you. Actually, this is my slide. So for this section, in order to actually visualize these cells on a rocket, we will be using the same LED UV light to actually get them to glow red, so we can detect their movement even without having a microscope on the camera, on the rocket. So essentially, all we have on the rocket is a little piece of camera, these cells, and the special compound, and ultraviolet light. And it turns out that the ultraviolet light can be used to detect the cells as well. So by tracking their movement, again, we can discover that movement phenomenon that we talked about before. Now is the time for the engineers to actually explain how things work. First up is Nathan Minnock.
All right. Thank you so much. Alrighty. So to understand the current design of the payload bay, we have to go back a little bit in time. So back in 2025, we of course participated in the Launch Canada Payload Challenge. Although the payload did get third place, there were lots of design flaws that we changed moving forward from them. As you can kind of see from the design, like the 3D print and all that, it wasn't exactly very great. How we mounted it was only through a singular threaded rod, and the assembly time was roughly around 30 to 40 minutes. And when you're in a rush on the advanced pad, that can bring a lot of issues. So one of the big things we wanted to change was we wanted to essentially make it so that we can easily slide the payload in, mount it quickly with 6 fasteners, and then we're done. That's it. Nothing more than 5 minutes, which is exactly what we iterated on, which I'll show in a few slides. Another thing we did was we had to change the camera, since essentially one of the big issues we had was that the camera essentially was, let's just say, not of the highest quality. It overheated, I believe, within 5 minutes of not even entering the rocket. It overheated on the table we were working on, which isn't exactly ideal for a payload that requires us to visualize things. To explain a little bit more of the design, we also did a biological payload last year, and what it was just a 3D print. It had 4 fasteners and a singular run cam. I believe it was the run cam thumb. And all it did was supposed to look at this vial, and this vial would glow in the dark when exposed to mechanical stress. And that was the whole idea. The camera, as I just showed off, was not exactly the most reliable, which we changed this year. We got a camera which had a very long runtime, doesn't overheat very easily, and generally speaking, just can get in focus properly, because that was another issue. The camera was too close to the vial, and we even gotten good footage anyways. So we kind of changed all of that moving forward. All right, so when we were starting to work on our latest payload, how we decided to run it was a little bit different. We decided to make a standardized slot within the rocket and say, hey, we want different parts of the university or different people or labs to essentially compete for the payload. We'll give you all the sizes, all the constraints, and you can submit to us what exactly you want to do for the payload. So as you can kind of see on the left-hand side, you have the flyer that we start spreading around campus. And from that, we managed to get 2 payloads. We got one from MyBar, Professor Ozzy's lab, and that's basically the dinos we're flying now. And then we also got the cosmic film payload, which you'll hear a lot more about in a few minutes. So that was kind of like how it went down for the early phases of the payload bay. Moving on, let's actually move on to the actual design of it. So within the payload bay, we have 3 segments. The very bottom one is the what I like to call the biomechanical segment. I'll talk a little bit more about that. Then there's the biovisual segment, which both these slots are related to the dinos that we're flying this year. Then above that is the cosmic film payload, which also will be discussed in a few minutes. As you can see, this design is very different from last year. It's not just a singular threaded rod with a G10 bulkhead. It's now almost completely CNC, except for the top part, which is a 3D print because it's non-structural. And then essentially everything's secured with 2 M5 fasteners. So we try to keep it simple and easy to use for the most part. All right, let's talk about the biomechanical segment. So, as you can see from the exterior, it's essentially a CNC-like part. So, like on the outside, it's all completely aluminum, except for the top part, which has a PCB, and the camera holder, the LiPo holder, which has a 3D print. Within that, we have a load cell. This load cell is designed to measure the axial loads of the vials while throughout flight. You can kind of see the load cell on the bottom right. Essentially, it's kind of secured with 4 M5 countersunk screws. And basically it's just kind of sitting there. To the bottom left is the 3D printed container. This container contains 3 vials, which has all of the dinos. So basically that container will be vibrating, moving around a little bit, and that's what we want in order to get the axial loads measurements. Then of course we have the piezoelectric cell, which is hooked up to the screw terminals on the PCB, which I'll show off in a second, which then is going to run all the way right next to the blue 3D printed container to give us those vibration readings. Moving on from that, we have our PCB. It's a very simple PCB, to be honest, but you don't need anything complicated for something like this. Essentially, at the bottom, you can see 2 screw terminals. This is meant for 2 piezoelectric cells, so that's what we have for that. Then to the right-hand side, we have 4 screw terminals. This is meant for the load cell. It's going to be amplified using a load cell amplifier, which you can kind of see in the centermost. And then above that is the BMP 390, which is a pressure temperature sensor, just there to essentially give us readings as secondary information. It's not flight critical whatsoever. Beyond that, that is primarily all there really is for the biomechanicals segment. I will now move it on to the visual segment, which my good friend Ito will talk about.
Hi guys, so this is the Dino Visual Segment Mechanical Design. So I came here today because I wanted to share a little bit about this project. I am a computer engineer, so I thought this would be a really fun challenge to take on. So essentially what it is Nathan's payload, or part of the payload, is measuring the vibrations and checking the vibrations, things like that. But I'm actually recording it. So we have a RunCam Orange in the compartment, and a UV lens in front of it, and then once we get to apogee, that PCB board you see on there will use 2 accelerometers to confirm we're at apogee, and then it will turn on a 365 nanometer light. So more on the PCB and system integration. So this year we really wanted to kind of go all out and make sure everything is perfect. It's perfect as it can be, because at the end of the day, this is about a year's worth of work for like 3 seconds worth of footage. We just really want to see what happens under these near zero gravity, 0G loads. So that's why on here we have 2 accelerometers, redundancy, we thought that was really important. We have an SPI flash, a buzzer just to ensure everything is on, working properly, and then we're using a LiPo to power the thing, so we have a MOSFET on there. All right, this is more of a personal thing, but I wanted to talk about the personal lessons. So as you can see, these are 2 of the previous designs. These are 2 of the prototypes that we went with in the beginning. These are not machinable. So I had to go through the process of learning, like, hey, what it means to get something on a CNC and get it machined. And now the first thing I learned from that is just be open to learning. You're gonna redo your design a bunch of times. It doesn't matter if you have to scrap it. Just have fun with it, learn, do as much as you can, and really just try to explore outside of your field. Just because you may be studying a certain type of engineering doesn't mean you have to stick with it. You can always go ahead, learn whatever you want, just enjoy it. And the next thing is, other than making it easy to manufacture, make it easy to build on the pad, right? I personally thought I wasn't, there may have been complications, you know, maybe our wonderful payload leads wouldn't have been able to be here. So we also did some payload instructions to make sure that any person can build it, you know? And this is the physical payload assembly. So I think it's really important just to kind of see, you know, the difference between the CADs and what it looks like on the computer, and then what it looks like in real life. I'm very proud of this project, and I'm very proud of the team this year. I think this was a wonderful learning experience, and thank you guys for having me on.
Thanks so much. So before I delve into about our payload, this payload, I need to give some context about the target of this payload, which is secondary cosmic rays. Every second, Earth is being bombarded with high energy cosmic rays, which sometimes they can go as high as mega electron volts. Well, thankfully, due to Earth's atmosphere, majority of these cosmic rays are being blocked. But what happens after these high energy cosmic rays interact with Earth's atmosphere? When they collide with atoms such as oxygen and nitrogen, a shower of secondary cosmic rays is formed in a process called spallation. As a result of this phenomenon, rare and unstable isotopes are emitted. Additionally, with these isotopes, we also have neutrons, muons, pions, neutrinos, and also gamma rays. The quantity of these particles, the abundance of them in these secondary cosmic ray showers, depends on their intensity, their altitude, and their energy and angle distribution. So you might be asking what is the point of detecting cosmic rays? Because apparently radiation from secondary cosmic rays is one of the main sources of natural radiation exposure to people, even on the surface of Earth. Even though it is non-lethal, but for people that are living at higher altitude or work in higher altitude, such as flight crews or people living on plateaus, they are more exposed to harms of radiation because of these secondary cosmic rays. Scientists have been trying to study and assess the level of danger these radiation from these rays have on human health. So this is the main equipment of this payload. So this payload is, another point of this payload is a diagnostic tool for the algae payload. The aim is to detect and study radiation from the shower of cosmic cluster. To measure radiation, we used a novel and an inexpensive radiochromic film, also dosimeter film, and it will be launched in two different looking payload equipments. One is a capsule, another one is a frame. These films were developed last year within the MEBAR lab. The longer this film is exposed to radiation, the darker it becomes technically. So these are the two parts of this payload. The external payload, also I call it the capsule, and the internal payload, which I call it the frame, simply enough. The capsule is designed to be hanged from the parachute rope, and it will be fully exposed to the outside of the rocket once the parachute is deployed. And fortunately, it has been designed and light enough to not cause any strains or any issues with the parachute process, within the recovery process. how it is designed is that the dosimeter film is supposed to be slide into the window right over there, and it will be fastened into the bottom of the bottom of the payload. The second part is the frame, which is going to be fastened on top of the payload bay beneath the nose, and this radiochromic film is going to be measuring the radioactivity from inside the rocket, and with a dimension of 40 by 40 millimeters. So one way that this project is going to be useful for the future is that it can give many preliminary information for the design and development of dosimeters for aeronautical application within aerospace, such as radiation detection for astronauts when they're in space. So, yeah. Thank you so much for your attention.
Any questions? Yeah.
Okay. Thank you all so much for your time.
Okay, thank you, Arbalest. We are looking forward to seeing your post-flight video of dinos happily glowing from their successful launch. I worry a little bit about Syed wearing sunglasses. Hopefully it isn't because you've made the dinos too angry. Our last presentation before our first break is from McGill Rocketry. Our presenter is Esteban Perot, who will be telling us about the team's latest, most powerful, and most ambitious engine. And in particular, the presentation will highlight some of the strategies that were used to overcome various challenges that were encountered while preparing for hot fire test. So please welcome Esteban to the stage.
Perfect. All right. If you could get the slides on the screen, that'd be nice. Awesome, thanks so much. Good morning. I hope everyone's doing well on this lovely, rainy Timmins morning. So today I'll talk quickly about scaling solutions for rocket engine testing, and particularly in the context of my team's experience. So to start off a bit with our team's background, we're the McGill Rocket Team, affiliated with McGill University. We were founded in 2014. We started off with some solid propulsion, so buying motors off the shelf. And then we started testing hybrid motors in 2018, just before the pandemic. And since then, we finally switched over to hybrid-powered rockets in 2022. And that's where we're at now. And this year's rocket is still powered by our hybrid engine platform. A bit about myself. I'm a fourth-year mechanical engineering student from McGill. I've joined the team in 2022, so it's been my fourth year in the team. I've been in various roles, mostly in propulsion, but now I'm in the role of the team's technical director, overseeing global engineering for the team. I also did a test stand capstone, a rocket engine test stand capstone for my team, so I'll talk about this a bit later on. And it's my third time at Launch Canada, so it's wonderful to be back here. And then another little fun fact, I'm also the motivational Peter on my team, so to make sure that our launch rehearsals are going well, we make sure that we have as much recreation as possible to get motivation from our troops. So for our team objectives, we're currently developing a new hybrid engine, and our goal is to massively increase our impulse class, so from an O to a Q up until like about 100 kilonewton seconds, so that we can reach the upper limits of the standard LC waiver with a single stage hybrid engine. So that brings us to a subject really of this presentation, which is how can one safely, cost effectively, and efficiently scale up hybrid rocket engine testing? So I'll start off a bit with our own engines. So a bit about our own sizing for this upcoming high thrust engines. So we started off with the platform of a nitrous oxide paraffin hybrid, which is what we've been doing up so far, being capable of reaching apogees up until 60,000 feet. This requires a peak thrust of up to 15 kilonewtons and up to 110 kilonewton seconds of total impulse, assuming a 150 kilogram wet mass. That requires about 45 kilos of nitrous oxide, 7 kilos of paraffin, up to 5 kilograms per second of oxidizer mass flow rate, and a 600 psi pressure, chamber pressure, so that we can get good efficiencies from our engine. That design was done via a combination of both common software like RAS Aero and HRAP, but also our own in-house code that was developed a couple years earlier that we use for hybrid engine iterative sizing and modeling. And so the overall scheme for the design starts off with our target flight profile, which then gives us an estimated component and propellant mass budget, from which then we produce propulsion simulations and aerodynamics optimization. Then we get into our flight simulations and we compare that to our initial target flight profile. And we iterate until we're satisfied with the results. So for the MRT hybrid engines, we currently have 3 active duty engines. The first one, which you see in the middle of the picture, is Maelstrom, which is the engine that we're using this year at our competition. So about 25 kilonewtons of total impulse. On the right of the picture, you have Hurricane, which is our upcoming high thrust, high potential rocket engine. So it's already been built. We have yet to test it, but it's coming very soon. And that one has the potential to go up until the full design parameter of 110 kilonewton seconds. And then on the left of the picture, we have what we call our bench scale engine, which is a much smaller version of Hurricane that I'll talk a bit later on in our slides. So now a bit about our own team's testing philosophy. So obviously high power engines definitely increase the risk in case of a failure. On a small test rocket, a small failure might be almost without any consequences, but with such a large engine, any sort of failure would potentially bring quite a lot of destruction and a lot of infrastructure repairs. More propellant also significantly increases the per test cost. So as you might have seen, the price of nitrous oxide bottles has risen so much in previous years. So that's another big challenge when we're dealing with our limited budgets. And finally, also at McGill, we have a context that is extremely low tolerant on risk. Basically, we've been told that any sort of engine failure would probably shut down our engine test site. So we're forced to err on the very cautious side of things, and we don't have that margin of maneuver that maybe some other teams or institutions have. And so to deal with that, we decided to subdivide engine component testing and start with low-scale tests to mitigate those risks until we bring everything together into our large-scale hot fires. So I'll talk quickly about our test stand. So for larger engines, we definitely required some upgraded testing capabilities. That starts off specifically for a hybrid engine with a larger oxidizer supply system that needs to be able to give out more mass at very high mass flow rates. We also need potential other testing features other than like a baseline self-blowdown. That includes pressurization capabilities such as supercharging the nitrous. We also need extensive instrumentation for data analysis, and that includes pressure and temperature measurements at a whole bunch of different places, as well as mass flow rate measurements to get accurate readings and compare that to our simulations. And then obviously we also need very high structural component ratings for those very high thrust values, because obviously that, like, as I was saying before, a failure, a structural failure specifically would be quite catastrophic to our test site. So overall, larger engines significantly increase the stakes during operations, and more things need to be planned beforehand. Just starting off with our plumbing and instrumentation, that's a diagram of our test site facility. So for the full potential of this larger engine, we will require 2 nitrous oxide bottles, mother tanks, that we will flip simply for economical reasons. Non-dip tube bottles are significantly cheaper than dip tube bottles, and so we made some flip jigs so that we can flip them. Then we have a nitrous oxide pump that will allow us to fully take advantage of those 2 bottles. Otherwise, we'd need like about 3 initial bottles, and that pump can help us really drive the very last of the mass into those bottles, into our run tanks, which have a 50 kilogram capacity so that we can test that full design with ample margins. And then in our nitrogen line, which is in blue above, we have a couple different features. So a purge line so that we can simply purge down our tanks at the end of our burn. But we also have a pressurization line, which allows us to do either continuous pressurization or supercharging, so like starting off with a 1 bit of pressurization at the start of the burn. That gives us the flexibility of testing different configurations for our engine if we do need to dabble into pressurization. And finally, we also have a mass flow meter into our test site, which I'll talk about slightly later. And we also changed our tubing to 1-inch diameter so that we can have low pressure drop up until 5 kilograms per second, which is the maximum target mass flow rate. For the thrust stand itself, obviously must resist the maximum design loads for this new generation engine at a very high safety factor that's characteristic of any ground equipment. So 15 kilonewtons at a factor of safety of 4, needed to integrate within our own containered test stand. And also we really wanted it to not have any setup needed to start testing, because any sort of setup obviously inevitably could lead to some errors. Someone didn't do a proper torque spec, forgot a certain thing. Over the years, some procedures might be forgotten. So specifically for the structural aspect, we really wanted to avoid any sort of setup, and we wanted to have this one-stop solution that stays there forever. And then, and so this design consists of welded tubing as well that is anchored into a very large concrete slab at the bottom of our container. And so the first way of testing that before going into our full thrust hot fires was simply to test it on our Maelstrom platform, which is the lower thrust, our current flight engine. So it went up until 5.2 kilonewtons, resisted perfectly, and so now we're very confident that there isn't any gross error into our design, and we're confident that we can continue on to higher thrust testing. So now that the infrastructure has been dealt with, let's dabble into exactly the engine side. So we'll start off with the injector characterization. So the oxidizer injector is simply one of the most important components of any hybrid engine. It needs to provide known mass flow rate as well as pressure drop into our thrust chamber. It effectively is a plate with multiple orifices that can be arranged in different angles and patterns, and each have very specific advantages. So on your right, you can see that there's different types of injectors, and each come with specific properties, or I'm going to say behaviors, inside of your engine. And so you can really choose your injector depending on the burn profile that you require from your engine, be it either like increasing your aggression rate, the mixing inside of your thrust chamber, or anything else. And so you can really fine-tune your engine via this injector. So the basis of modeling usually starts off with this single-phase incompressible model. So you have the equation here on your screen, and what it says is that your mass flow rate is a function of the injection orifice area, the fluid density, and also the pressure drop through your injector. However, very important, there's another factor, it's a fudge factor called the discharge coefficient, which takes into account the compressibility, the flow separation inside of those narrow channels. And that really depends on the exact injector geometry and flow conditions. And so it's very specific to every injector configuration. And it's not something that you can easily predict. Maybe you can do some complex CFD, but there's always some complex other real life stuff that comes into it. And so it's a very empirical factor. But given an injection area, fluid density, and by measuring mass flow rate and pressure drop, we can find that discharge coefficient. So that's what we did. We developed an injector test rig, dedicated test rig specifically to test these injectors and to estimate our discharge coefficient for these injectors. So it uses water with nitrogen pressurization so that we can exactly fine-tune the pressure and the blowdown of our setup. We measure the pressure drop and the flow rate. And overall, that allows us to get much faster, cheaper, and safer runs than doing engine tests to obtain specifically that coefficient. Now, what did the data tell us? So on your top left, you can see the experimental results, and we found an experimental value of 0.67 as our discharge coefficient, which is very close to the theoretical value of 0.65 you see on your right. That is characteristic of straight hole injectors. So we were very pleased with that result. The model corresponds very closely to what we found. However, now we compare that to our engine testing results, and the data is not in agreement anymore. So our CD, experimental discharge coefficient, now is about 0.35, which is about half of the value we found with our injector test rig. So that's mainly due because nitrous oxide strongly behaves as a two-phase flow, and definitely not as an incompressible flow, which is what water is, and which is the baseline of the discharge coefficient methodology. And so there's other physics that impact the sizing of a nitrous oxide injector. So it's really a specific thing linked to our oxidizer. And so to solve that issue, we introduced a model correction. So the two-phase flow reduces the effective mass flow rate, but we have other models that can solve this issue, specifically one called the Dyer model, which takes into account thermodynamics of the vaporizing gases. I didn't put here the formula because it's much longer, much more complex than the single-phase incompressible model. However, it takes the thermodynamic phases before the injector and after the injector, and that allows you to better estimate your real pressure drop and mass flow rate. So what we did is that we implemented a code that takes into account those different parameters, as well as our estimated combustion chamber parameters, and that allowed us to basically translate incompressible discharge coefficient into estimated nitrous oxide performance. And so overall, we managed to achieve a system that we can test very fast and efficiently with water, and then translate this data for nitrous oxide. Now we dealt with the injector, we'll go a bit into the combustion characterization. Here we go. So there's a couple important parameters that we want to characterize. There's combustion efficiency, which is a function of the internal ballistics of the engine, the fluid flow, the chemistry, and the internal ballistics themselves are dependent on a couple other parameters such as regression rate, fuel geometry, which give us our mass flow rate, and as well as our fuel blend, which affects the total energy density inside of our thrust chamber. So specifically for combustion efficiency, it's a ratio of how much chemical energy we're able to release compared to the absolute perfect scenario where every single molecule combines and releases the energy. And so it's the ratio of our characteristic velocity, or our actual characteristic velocity, to our theoretical characteristic velocity. And the actual value can be measured using pressure and mass flow rate, and the theoretical one is based on theoretical thermodynamics of the combustion. So the couple relevant parameters here are our oxidizer injection method, the atomization, spray pattern mixing inside the chamber, we have the combustion pressure, the higher the pressure, the better the mixing, and there's also our fuel composition, which can affect the combustion itself, and also our chamber geometries. So the longer length you give your combustion products to fully react, the more residence time they'll have to actually fully mix and combust. So here's our baseline and expected outcomes. In our case, we're limited in terms of combustion chamber length by our fin can length, which is due to our manufacturing processes. So to move onto this larger engine, we had to simply increase the outer diameter. However, that means that every single dimensions change. Effectively, our length to diameters decreased a lot compared to our original engine. And so you see on the bottom of the table, our post-combustion chamber on Maelstrom, the length to diameter was 3, which is extremely long and gives a long time per pound to mix, and gave us a very good 95% estimated combustion efficiency. However, for Huracan, that length to diameter ratio is only 1. And so that means that we'll likely have on this baseline a much lower combustion efficiency. And so we'll have to innovate in terms of our injector design and our fuel blend to keep up that efficiency high and make sure we don't leave unused propellant on the table and don't waste any mass. That's where we take the bench scale engine that I showed a couple slides earlier. It's effectively a 1/20th scale of the large scale engine, which has the same internal proportions, so length to diameter ratios of the chamber, the spacers, and whatnot. It's a very much like only test hardware, definitely not made for flight, but it has a lot of instrumentation options because that's the goal, it's to get data. So you can see on the bottom we have like axial and radial tapping ports that allowed us to get temperature and pressure data. And then for that bench scale engine, we needed a dedicated test stand that would allow us to get the testing cadence that we needed out of it. And so that was actually my capstone that I did. And we effectively made a vertical test cell to test that engine in a vertical position. It uses passive anchoring via the engine's plume that gets reflected off of the triangular deflector plates. And it's mobile modules that allows us to easily transport everything. And so overall, the anchoring requirements are quite low, and that allows us to test about like anywhere with very little anchoring because it self-anchors. The operations are very cheap because we simply use whatever's left of old bottles from previous tests. So it's effectively almost free nitrous oxide. Has very rapid turnaround time, about like 1 hour between tests. So we can get up until 5 engine tests per day, which is effectively an entire test campaign to what the team has been doing before. Usually we got around like 5 to 10 engine tests over an entire year. And this time around, we could get the same amount of tests in 1 to 2 days on this very small engine. So that would allow us to get actual combustion performance metrics at much smaller scale that's much safer, faster, and efficient to run. For the exact objectives that we want to get out of this bench scale, it's simply to characterize the regression rates of different fuel blends, to compare performance of various injectors, and also for every single test, we want to estimate our combustion efficiency and our specific impulse. And all of that will give us qualitative design improvement metrics, such as which fuel blend is more energetic and gives us the best performance, the best injector geometry. So for example, does this injector geometry allow us to increase our fuel regression rate to get higher thrust, or would this one give us better specific impulse because there's better mixing inside of the chamber? And all of the best, only the best like results would actually be implemented into the large scale engine, and they're qualitatively be measured and improved. So a few concluding remarks is that overall testing infrastructure is a significant preliminary hurdle that blocks the initial testing of these large-scale engines, and so that needs to be thought of very much in advance. It took us an entire year simply to set up our test stand without any actual testing, and so it's a very significant amount of time and logistics to set up. And then our strategy to mitigate the risks linked to very high power engine testing were to separate a couple different parameters and test those individually so that we save time, money, and resources on the big engine testing. So that's what we've been throughout the past year, and we'll be ready to test this big engine pretty soon next year. And then obviously the small scale testing is very important so that we can get those couple data points early on and then know what we're dealing with on the higher scale engine. So now I'd like to thank all of our sponsors that allows us to be here, as well as the fantastic job of our propulsion and launch systems team, whose work I kind of gobbled together and presented here. That's very much appreciated. Thank you so much for your attention. Now I'll take some questions if there are any. Yeah, that's a great question. So initially, what we started off with was very simple. The question was, what software did you use to simulate your hybrid engine? Originally, we used very simple hybrid engine formulas, the sort of things you find in rocket propulsion elements. That's very much the baseline. That's what we started with in our very initial testing in 2018. When we started switching to our competition rockets in 2022, one of our team members developed an in-house software that basically combines all of these equations and modeling into something that allows us to run all these calculations much faster. And so instead of taking like a couple weeks to run like a design point, you input everything in a code, and that allows you to run these simulations much faster. And then that was in 2022. I think since then, there's been another software that's been publicly released in about, I think, 2024. It's called HRAP, Hybrid Rocket Analysis Program, which is effectively the same thing. It takes into account, it models all of the engine for you given a set of inputs. Obviously, each of the models have their own like limitations and assumptions that you need to be aware of. And we still use both software because specifically our in-house software is pretty good at iterating, at sizing the engine. So for example, we want a certain, we give it a flight profile, we want a specific altitude, and then it iterates through different propellant combinations until it finds a good one that allows us to reach that flight performance. And actually, that software is like, it's mostly ready into like an app. So we'll see, maybe that might be a future thing to release it. But there's existing software that allow you to go through these different parameters and do those calculations very fast. Though I really encourage you to like read off all of the theory behind it, because definitely the hybrid is a bit more complicated and has a lot more simplifying assumptions than the more established like solids or liquids. Of course. Thanks so much.
Thank you, Esteban. That was an excellent presentation. I'm sure the McGill team is very grateful for your motivational energy. And I actually have some awesome photos of your team from last year, just showing how incredibly supportive you all are when faced with very stressful challenges. You're an amazing team. Okay, we're going to take a break, and we will be back at 10:45 for our next student talks. So just a reminder as we begin this next section of student talks, if you have questions to please use the microphone. I think that microphone over there, yep, the left hand, the one that I'm facing on the left is the one that is working. And presenters, if the questioner does not use the mic, please remember to repeat the question. For the live stream audience, we would really appreciate it. Okay, here we go. Our next presenter is the propulsion lead from Waterloo Rocketry, Thomas Fairhead. Waterloo expanded from hybrid propulsion into liquid rocket engines in 2024 and have now had 2 successful liquid rocket flights. With that success under their belts, Thomas is going to tell us about the evolution of their liquid rocket program up to their 3rd liquid rocket to be launched this week with a target altitude of 63,000 feet. And Thomas is also going to tell us if he had to scrap the entire program and start over, what he would do differently. Thanks very much, and please welcome Thomas to the stage.
Okay, hi everyone. I actually slightly changed my presentation. Originally, it was more program management focused, but our project management kind of sucks. So I decided instead it would be more useful to basically go through what I thought were the most useful things and tips and tricks for if we were doing liquid rockets again. So it's kind of just a collection of useful technical information that, if we were doing liquid programs or if, you're looking at doing a liquid program, you might find helpful. So just to give a little overview of what we've done on liquids, why should you listen to me? Waterloo Rocketry Liquids program, I would say, has been reasonably successful. We started 3 years ago in 24. Since then, we've flown 2 liquid rocket flights successfully. The asterisk is because we never seem to get them back. But the propulsion seems to work pretty well. In 2024, we flew to 20,000 feet approximately. In 2025, we did 38,000 feet. And in 2026, we're trying to go higher than 60,000 feet. In those 3 years, we've done 7 full-scale engine tests. 6 of those were successful. We also did a regeneratively cooled hot fire. We did a TVC hot fire with LOX. I've done a little liquid hot fire as well. And through that time, we were the first amateur liquid rocket to fly in Canada, and we currently have the 4th highest amateur liquid rocket flight in the world. So you can still think that my ideas are terrible, but yeah, it's worked out pretty well for us. So what kind of engines we build nitrous oxide liquids. Nitrous oxide is the oxidizer and ethanol is the fuel. These are by far the simplest propellants you can choose. If you're going to start with liquids, 80% of the time you should pick nitrous oxide and some kind of alcohol. It's the easiest way to get started. For pressurization, we do vapor pressure blowdown, and we use a concentric fuel tank with a piston to pressurize the fuel. This is also really simple because it means you don't need extra pressurization gas. Our combustion chamber is ablatively cooled. It's got a graphite nozzle, and we make our injectors with metal 3D printing. We light the engine using a solid propellant puck, and every valve on our rocket is custom at this point. So generally, we tend to not build the most complicated rockets, and I highly recommend that if you're going to do liquid rocketry, you start as simple as you can and progress from there. You'll find that it's a pretty difficult challenge once you get going, and just getting started is hard enough. How do you actually choose an engine architecture? One of the questions that I get asked a lot is, why do we operate our engines at such a low tank pressure? So we operate our engines at 650 psi, which is only about 15 degrees Celsius for the nitrous. Now, obviously, we could heat to a much higher tank pressure, and if you look on the left, the graph of tank pressure versus specific impulse, as we increase the tank pressure, the efficiency of the engine gets higher. So you would assume that you would want to make your tank pressure as high as possible because that's going to get you the most efficiency. The problem is that your oxidizer gets less dense as you heat it up, and that trade actually pushes you towards a much lower pressure than you might think. So here's a graph of the delta V of a reference propulsion system with tank pressure and delta V on the y-axis, obviously. And you'll see that it actually tells you that your tank pressure should be like 400 psi. Now, the issue with running such a low tank pressure is that it's hard to make an efficient engine when it's running at low pressure. The efficiency of your engine, combustion efficiency is somewhat proportional to chamber pressure, and if your chamber pressure is too low, you're going to have a hard time making it efficient. So we ended up a little bit higher pressure, but in general, as long as you can keep your efficiency high, running a lower tank pressure is actually better for performance, up to a point. And that's also nice because it means that you don't have to worry about making all your stuff rated to super high pressures. So yeah, if you're just starting out, I would caution against just chasing the highest tank pressures and the highest specific impulses because it doesn't really help you that much. Okay, moving on to what is probably the most important part of liquid rockets. Generally on nitrous rockets, the only part of the rocket that moves is the valves. And so therefore they end up being one of the hardest parts. And it's probably the part that we get questions about the most at Waterloo Rocketry. So Waterloo Rocketry, we've been building custom valves since the hybrid program. At this point, every valve on our rocket is custom. And I think there's a lot of good lessons to learn from what we've done. So the first kind of real custom valve that we did was in 2023 on the hybrids program, which was an oxidizer valve that's called a coaxial sleeve valve. Basically, the way this valve works, and I have a closed and open diagram there, but there's a sleeve, and you drive the sleeve back and forth, and the big advantage of this kind of valve is that the propellant gets to flow straight through. So it's like a ball valve, but the difference between this and a ball valve is that a ball valve, you need a rotary actuator, which ends up being really big and taking up a lot of space in your rocket. With this kind of custom valve, you can make it much, much, much smaller because you pilot it with gas. Now, this valve had some issues. The biggest issue with this valve was that because the seat of the valve, which is the white Teflon bit that the sleeve is sitting on, because that was a conical seat, basically the concentricity of the valve sleeve and the seat was a critical dimension. And that caused us a lot of problems where if it wasn't sitting perfectly concentric, it would just leak through one side. So that's kind of the first big lesson, is that conical seats are fairly difficult to make work, especially on a big valve. So in 2024, which was the first liquid, we still use sleeve valves, and they look pretty similar to the previous ones. But the difference is that we switched them to using knife edge Teflon seals. And a knife edge basically just means that you sharpen the valve sleeve to a point, and it presses into the Teflon instead of seating on an angled surface. And there's two big advantages from this. The first one is that your PTFE piece is now just a flat piece of Teflon, and that means that it's much easier to make, and it means that when you wear it out, because you will run through them, you'll put nicks in them, you'll scratch them, and they won't seal anymore. It's very easy to replace. And it also means that the concentricity of the valve sleeve and the valve seat doesn't matter at all, because it will still seal even if you're off-center. And so that leads to the second lesson, which is that generally any of your sealing surfaces, don't make them in aluminum. So the first time we did this, we made the valve sleeves in aluminum, and within the first day of testing, the valve sleeve had gouges in it, because if there's any FOD or anything, you're going to put a scratch in the valve seating surface, and then it will no longer seal. So all of your sealing surfaces, you should just make them in stainless steel. The mass penalty is not that big, and it will save you a ton of time remachining sealing surfaces over and over again every time you scratch them. Now, we also do a bunch of other kind of valves on the rocket. So for fill valves and for vent valves, we tend to do poppets. These are from 2024. These are also actuated pneumatically. So all of the valves up to 2024 were actuated with low pressure nitrogen. Pneumatic actuation is great, but it means that you have to carry nitrogen on your rocket. And what I say the first lesson was, we want to try to keep the rocket as simple as possible. So starting in 2025, we basically went looking and said, hey, is there an easier way that we can do these valve systems? And the answer is yes, there are simpler ways you can do it. So The valve system that we're using on this year's rocket is very similar to the valve system we used in 2025. This diagram maybe looks a little bit confusing, but essentially the way it works is that while the quick disconnect is attached, your ground supply of nitrous oxide is connected to both the tank and it's connected to the pilots of the valves. So as long as your tank is pressurized and your quick disconnect is attached, your valves are being held closed. And this means that you don't need any electrical control of your valves. You don't need any, like big actuators or solenoids to control pilot gas. You just start filling propellant, and the pilot volume will just come up to pressure naturally and hold the valve closed. Then, when we disconnect the quick disconnect, the pilot volume is outside of the seal. So as the quick disconnect comes off, there's a little tiny poppet that seals off the tank. So obviously you don't want to dump your whole tank when your quick disconnect comes off. But when the quick disconnect comes off, we do want to open the valves. So there's a separate little pilot volume that basically vents the area underneath the valves. And in doing so, it means that we don't have any control of the propulsion system on our rocket anymore. So all that control is offloaded to the ground, and that means that your rocket can be simpler, your valve bays can be smaller, and there's much less that can go wrong in a situation like this because everything is just controlled mechanically. So if you have an electrical failure, you can still abort your rocket, and that's actually really important for safety. If you have questions about this valve concept, I'm happy to answer them after or just come find me. I think I'm very proud of how this works. I think it's quite high performance and quite safe as well. But it is like a little bit complicated to set up in terms of just understanding how it works. So yeah, why should you do custom propellant valves? Because obviously you walk around the room and some teams have their own valves, some teams are using commercial off-the-shelf valves. What does that trade actually look like? Custom propellant valves have big advantages in terms of form factor and size. They're generally much smaller. They also end up being a lot lighter. Also, you might think that making your own valves is unreliable. That's not necessarily true. Making actuators for commercial valves is a challenge in itself, and doing your own valves, you can make them just as reliable as any commercial ball valve. They also end up very cheap if you machine them in-house. Big commercial actuators and ball valves are quite expensive, and aluminum stock and Teflon is not particularly expensive. Generally, they can simplify your control architecture as well, and they're a really, really good project to start learning about how to design fluid components. However, it does come with a disadvantage. The main disadvantage is that it's a bigger time commitment. You have to spend more time on this project versus if you just buy a valve. And generally, you can end up with more leaks than commercial off-the-shelf alternatives, especially on early iterations while you're still trying to figure out how much sealing force you need. And you have to test them a lot more, obviously, because they're custom. But in general, I think that custom propellant valves are a very good project, and even if you're just starting out with liquids, it is worth looking at because trying to fit commercial valves into your rocket is actually a much harder problem than you might initially think. Okay, so you have your valves, you open your valves, and you're time to light your engine, and then your engine explodes. That's the one static fire that we failed. It's generally what in the liquids world you'd call a hard start. And generally, the golden rule for making sure your engine lights properly is to never lead fuel, okay? If you ever lead fuel into the chamber, your engine is pretty likely to explode. Now, there's lots of ways you can make sure that you never lead fuel into your chamber, but I highly, highly recommend, and we've always done this at Waterloo Rocketry, that your propellant timing is mechanically controlled. So you don't want to have two valves and control the timing with electronics because electronics are unreliable. If your valves, one of your valves is sticky, it might not move when you say you want it to move. You want them to basically be mechanically set up so that one of them has to open first, and that's your oxidizer valve. So there's a bunch of different ways you can accomplish this, but in 24, we did this by basically just having a different length of feed system between the two valves. So the oxidizer valve was very close to the engine, the fuel valve was farther away, and we actuated them on the same pilot line. So both valves were given nitrogen gas to open at the same time, and because the fuel valve was further away, oxidizer always went into the chamber first. In 2025 and 2026, both valves are beside each other, so we couldn't use distance anymore. And so what we did instead is the fuel valve has a bias spring. So both of them still vent out of the same volume, so the gas to control the valves still moves at the same time. But the fuel valve is just set up with a spring so that the fuel valve takes a little bit longer to open than the oxidizer valve. And I highly recommend some sort of similar approach to this, because it's very, very easy if you have two different valves that are controlled differently for one of them to end up off timing and then your engine to just explode. And the worst feeling, I can tell you, the worst feeling is doing all that work to build the engine and then turning it on and it blows up. And you don't even get any data. The other thing is actually, what do you use for an igniter? So how do you start the engine? Waterloo Rocketry, we've been using RNX puck ignition for probably almost 10 years at this point. And I don't have any wood to knock on, but it has never failed to light an engine. The way it works, you just take potassium nitrate and epoxy, and you basically, you basically cast them into a, okay, hopefully my battery doesn't run out. You basically cast them into a puck at the top of your chamber. Now, this puck needs to be pretty big. I don't know if the clicker's working. You may need to close that prompt. Hopefully my battery survives. Anyways, but yeah, you can see that the gray puck at the top of the chamber is the igniter in our rocket. It's pretty big relative to the chamber. There's really no reason to make it small. If you make it really big, you're basically guaranteed to light your engine every time. And the way we make sure that that lights reliably is we actually embed the igniter, which is a wire of nichrome, into the propellant. Now, anybody who does solid motors is probably dying inside because I just said that we attach the igniter into the propellant and there's no way to remove it. But on a liquid, you don't have to worry so much about that as a safety hazard, because on its own, this igniter just makes really hot fire. It will never generate any pressure. It will never blow anything up. It's just a lot of heat. Obviously, you don't want to set it off, so you still want to follow igniter best practices. But yeah, you don't have to worry so much about this being a huge safety hazard, other than it starts a pretty vigorous fire. And if you're wondering, that's why we always end up outside of the conference center at these conferences, because the igniter is bonded into the liner. So yeah. Okay, I can't do a liquids presentation without talking about injectors. I'm not going to talk too much about this, but in 2024, we tried to do swirl injectors, and swirl injectors are a fairly attractive thing that you might think are good to do. I thought so when we were starting out. But they're not as easy as you think. And these injectors had a pretty meh performance. They were not that great. And the reason for that is that when you use two-phase propellant, so when you use nitrous oxide, you should be able to just charge it with USB-C. Okay, pause. I'll just keep talking. Basically, when you use a two-phase propellant in a swirler, as soon as the nitrous oxide gets into the swirl chamber, it's going to start evaporating. And as it starts to boil, any of the momentum you gave it for swirling is just going to get basically canceled out because there's so much turbulence. With water, we were getting like perfect swirl cones that were the exact angle we wanted. And as soon as we put CO2 into the system to test it, it just no longer worked. And that basically killed the efficiency. If you want to do swirl injectors, I think you can. But it ends up being a much more complicated project because you have to account for the density change of the nitrous in the swirl chamber, and that's a pretty difficult thing to model. So instead of that, we tend towards impinging injectors now, and impinging injectors are much easier than swirl injectors. The biggest advantage of an impinging injector is that you can have really long holes, and nitrous oxide has and I'm losing my slides here, but yeah. Nitrous oxide has a really interesting phenomenon as a two-phase propellant, where basically, if you have enough pressure drop and your holes are long enough, the same way that in a nozzle you have choked flow, if you have a long enough injector and you have enough pressure drop, the vaporization of the nitrous oxide in the hole will, the amount of vapor in the hole will basically create a choked flow condition, just like a nozzle, but in your injector holes. And this is hugely advantageous. Generally, this means that when you do a cold flow in atmosphere and you do a flow into your engine, you're going to get the exact same flow rate, as long as your engine pressure drop is high enough. And when you're trying to characterize your engine and trying to figure out how much flow you have in your injectors, this is pretty much the best case scenario, because you don't have to do any math of, how does my flow rate change when I operate it in the engine? Is it going to behave differently? Once it reaches critical flow, that's how it will behave, and it will continue to behave like that even as you increase the pressure drop significantly more. With swirlers, it's much harder to get long holes. It's kind of the same thing on a pintle, but when you're doing impinging injectors, you can pretty easily have holes with an LD of like 10, LD being length to diameter ratio of the hole. And once you get up to like 10, 12, you end up getting really, really easy to characterize flow rates. Hopefully my laptop turns back on soon, because my next slide has pictures. Yeah. I can keep talking, but I think I'm just going to lose everyone without visual aids. Does anybody have questions up till now while we wait for the slides to come back on? Oh, hang on. I got to go put in my password. Okay, here's a good picture of what I was talking about with regards to the swirlers. This is the same swirl element. On the right, it's tested with water, and on the left, it's tested with CO2, which is the inert analog to nitrous oxide. And you can see that with water, it makes a really nice spray cone, and with CO2, it really doesn't. So that's why I don't recommend doing this unless you put a lot of time into modeling. Here I was talking about two-phase flow and having long injector holes. Now we're tending towards impinging injectors, and this is what our injector looks like this year. It's all 3D printed, but you can see that it basically is just a bunch of holes in a plate. This is why impinging injectors are pretty easy, because you generally just have to figure out a way to make angled holes, and you can 3D print it or you can drill them. And it doesn't require any super advanced manufacturing techniques to do. So I talked a lot about two-phase flow. Nitrous oxide is a bit of a hard propellant to model because of that two-phase behavior. When you're modeling fuel, it's really easy. It's single-phase incompressible. If you go into any fluids textbook, it will tell you that orifice flow equation for single-phase incompressible fluids. But as you get towards nitrous oxide, that equation stops applying because, like I was talking about, you can't just keep increasing the pressure drop infinitely and keep getting higher and higher flow rates. And so that's where models like homogeneous equilibrium or Dyer come in. I don't really want to get into that for this presentation, but it's kind of just a demonstration of what I was talking about where with the models that aren't single-phase incompressible, the flow rate basically caps off at a certain point and it won't increase anymore. Now, flow modeling is probably the question that I get the most, especially from American teams. Now, you guys aren't Americans, but given that I get this question so much, I thought I would basically give a quick little primer on how we do mass flow rate measurement, because flow meters are really expensive, and if you're starting a liquids program, you might look up and say, okay, I need to measure mass flow rate into my engine. How much does a flow meter cost? And you're going to see that a nice Coriolis flow meter is going to run you $30,000. Now, I don't think anybody can afford a $30,000 flow meter. Also, Coriolis flow meters don't deal with two-phase flow particularly well. So even if you spend $30,000 on a flow meter, it's probably not going to work. And unfortunately, you really need to know the flow rate in your engine because it's basically one of the most important performance parameters. Now, you can hang your tank from a load cell or build a thing with load cells, but we have found that that's actually a fairly long engineering project because there's a lot of vibration. You can see that there was an example of us trying to get load cell tank mass data. That data has a ton of noise, and also After the burn, it ended showing that the tank mass was 10 kilos lighter than the tank was. So the accuracy is highly questionable. And so if you can't use a flow meter and you can't measure the mass of your tank, how are you supposed to figure out what the flow rate in your engine is? Well, this is I call it the cheap mass flow rate measurement method that we use at Waterloo Rocketry. Is it the most accurate? No. But is it the cheapest and easiest way to do it? I think so. This method, you only need to use pressure transducers, nothing else. The big assumptions that we're making when we do this is we're assuming that the flow rate model that we're using, so whether we're using like homogeneous equilibrium or Dyer or single phase incompressible, we have to assume it's reasonably accurate. And we have to make an assumption that nitrous oxide is in saturated equilibrium, at least in the tank. That tends to be a very good assumption. If you set up a simulation of the behavior of the nitrous oxide pressure if it was at equilibrium and you plot it against what you actually get in test data, it tends to be pretty much bang on. So how do we actually do this? Well, the first thing, and I'll go through examples after to kind of show you how. First thing, you need to know how much propellant mass you filled into the engine, and you need to know when the propellant runs out in your tank. You also need to have a flow rate model that you think is reasonably accurate for your propellant. For fuel, you can just use single phase incompressible. For nitrous, we tend towards homogeneous equilibrium. Then you basically need to calculate mass flow rate at every timestamp of your data. And now you might be thinking, well, we don't have a discharge coefficient because obviously we're trying to find mass flow rate. But you can calculate mass flow rate without the experimental discharge coefficient. It will be wrong, but you can still calculate it. And then you can do a numerical integration of that mass flow rate across the whole data set, all of the time that the propellant is flowing. And by doing that, you're going to get a total propellant mass. It's not going to match the total propellant mass that you put in, but you're going to get a number. And then what you can do is you can just match the discharge coefficient such that the total propellant mass that your integration gives you is equal to the propellant mass that you know was in the tank. And by doing that, you're going to get a reasonable guess of what the flow rate in your engine was at every point. So how do you actually do this? Fuel, it's really easy. On a liquid with an alcohol fuel, you tend to just load fuel by hand. So you know how much fuel mass you put in the tank. You just weigh it, or you measure it by volume when you put it in. How do you know when you ran out of fuel? It's also really easy. So this is a pressure data from one of our static fires. You can see that the fuel tank pressure is on the orange line, and as soon as the piston bottoms out in the tank, you're going to have no more fuel pressure because there's no more force driving it. And so at the moment where the piston bottoms out, you know exactly that that's when you ran out of fuel. And so you can just run this with a single phase incompressible model of the tank pressure minus the chamber pressure, and you can get a pretty good guess of what the fuel flow rate is at any point during your burn. This tends to be fairly accurate. In 2024, we thought we would go to 20,000 feet, and we went to 19,000 feet. So you will get a pretty good performance curve for your engine if you do it this way. The nitrous oxide side is a lot harder, and the reason is that you can't just measure how much mass of nitrous oxide you put into your propellant system. You can't walk up to it. You're filling remotely. So how do you do it? Calculating the filled mass into your tank is reasonably simple. You can just do it by using the pressure that you filled at, where the dip tube is in your tank, and the tank volume. This is just a saturated equilibrium calculation. You can learn about this in any thermodynamics class. When you want to calculate how much when it runs out, I tend to only use this model when there's liquid nitrous oxide in the tank. And figuring out when liquid nitrous oxide runs out is pretty easy. The reason is that while you're flowing liquid, the liquid is boiling off to keep the pressure. So your pressure is dropping pretty much linearly. And so that's a nice straight line on your pressure curve. But as soon as the liquid runs out, now it's just gas, and it's going to be an exponential decay, right? And so there's a pretty obvious knee in the data where those two curves meet, and you can basically point that out and say, that's the moment when I ran out of liquid nitrous. Now, that doesn't mean you fully ran out of nitrous oxide, because there's obviously still vapor in your tank. But it's pretty easy to calculate how much residual vapor mass there is, because at the instant where you run out of liquid, at that exact moment, your tank should be 100% saturated vapor. So it's still a saturated mixture, but it's with, I guess the quality is 100% if you were doing it like a thermodynamics class. And so given that, you now have how much mass you started with, and you have how much mass you ended with when you finished burning liquid nitrous oxide. And so then using those two numbers, you can do the integration method that I was talking about, and you can calculate flow rate over time. For us, the homogeneous equilibrium model tends to give the best results. And the reason for this is that we have very long holes and we have a high pressure drop. So you're very, very close to ideal choked flow in those injector holes. If you did something different, you might end up with a little bit of a different model that is the most accurate, but there's a lot of resources online about modeling two-phase flow in orifices, and you guys can do your own research to figure out what model best fits your data. But homogeneous equilibrium is a pretty good place to start. So hopefully that wasn't too technical for everybody. This is like probably the question that gets asked of me the most, and I have to explain it every time. So if you have questions about this, please, you're more than welcome to come talk to me. I'm happy to kind of go over more about how this works, or I can send you the Python code that I use to do it. And yeah, so some final thoughts about liquid rockets. Liquids are hard. I've just kind of brushed the surface with this presentation of various topics that people ask me a lot about. But liquids are also really fun. It's really satisfying to make your own engines. And as of today, they're a lot easier to get into than they used to be. We're kind of in like the heyday of amateur liquid rockets. Groups like HalfCat have fully published open source liquid rocket engine designs that you can go download off the internet, and they've got a 200-page guide that you can read about how to build it and how to use it. So given all those resources, I really think that if you're thinking about doing your own propulsion system, now is really a good time to get into it. And if you're curious about doing liquid rockets, please reach out. We have a lot of technical documentation on our website. And also, I'm always happy to get on a call or just answer your messages about any questions you might have regarding liquids. You can also find me at the booth after. I really think that although it's a harder challenge, it's really worth doing. And you're going to learn so much if you do it. So yeah, does anybody have any questions? Thank you, I guess, yeah. We got some questions.
Hi, I just started the presentation saying that we're going to change our talk about project management because we're happy with how well it was done. But would you still be able to share any lessons you guys have learned in that time?
Yeah, sure. Yeah, I mean, I think. So the reason that I said our project management is bad is because our project management tends to end up with a few people on the team working 40 hours a week the entire year to make the rocket work. Now, I think that not every liquids project will need to be that long. I made a personal liquid rocket in one summer, so it doesn't need to be a super long and terrible process. But for us, I think the biggest lesson learned is that you can't just every year we tend to be we're just going to improve the system from last year, and then we end up just saying, we need to fix this valve, and we need to fix this valve, and we need to fix this part of the propellant tank, and we need to upgrade the injectors and upgrade the combustion chamber, and then you look at it and you've just said that we're going to rebuild the entire system and it's going to be brand new every year. And that is really hard to do. You end up at the end of the year with a bunch of stuff that got half finished or a bunch of half upgraded projects where it's still not as good as you wanted it to be. So, if I were to do it again, the biggest thing I would do is just do it bit by bit. Start with, just doing a few things. So, maybe you don't make flight propellant tanks. You use commercial off-the-shelf valves for your first hot fire, and just focus on the combustion chamber. And then, the next year you say, okay, now we're going to do custom valves. And then the year after you say, okay, now we're going to make upgrades to our combustion chamber. And I think that doing something like that will help a lot with the project management because, our strategy of upgrading everything every year has tended to make us both late and lose a lot of sleep trying to get everything finished. But yeah, I would say that I think that the hardest part about project management is to not just end up in a case where you have a few people on the team that are trying to do everything and spending all their time just working on the rocket and not even being able to go to class. So I think the most important thing is delegation and trying to keep your scope reined in. I kind of emphasize that our system is actually pretty simple when you look at it, relatively speaking, for liquid rockets. We tend towards a simple solution, and I really think that that's like the most important thing you can do. You do not need to make it super complicated. You can get really good performance out of simple systems. Any complicated thing that you add is going to be extra weight on your rocket, so you have to even figure out if it's worth it in the first place. But yeah, keeping it as simple as possible, especially when you're starting, is good, because you don't want to end up like me and doing 80 hours. In 2024, it was like probably like more than a full-time job the entire school year, and yeah, I almost failed some of my classes, so don't do that. Yeah, the cost is a really big sliding scale. So our rocket is huge. Our rocket this year is a giant rocket. We've probably spent upwards of $50,000 on it, but it doesn't have to be so expensive. The personal liquid that I built, so it's 3.5 inches in diameter, so it's sort of like the size of a 98 millimeter solid. That project probably cost about $3,000. Now, I would not take that number as how much it's going to cost you, because by the time I was doing that project, I had built a bunch of liquids before and I had learned a lot of lessons. So I basically made everything once and it all worked the first time. That will probably not happen on your first one, and it definitely didn't happen for us on the first one. So I would say that I think you can reasonably make a small liquid rocket for under $10,000. If you follow the Half-Cat guide, you can do it for under $5,000. Because that system, they tell you everything to buy. It will not cost you more than $5,000. But if you, obviously, as you start to scale it up, it's going to start costing more and more, especially if you can't machine parts yourself. Because you're outsourcing large machine parts starts to get really expensive really quickly. But if you're just doing, making a smaller one, which I think is probably where you want to start anyways, I'm reasonably confident that you can do it for under $10,000. Yeah. Alrighty.
Thank you for the excellent questions, and thanks again to Thomas and Waterloo Rocketry for sharing your team's journey with the many teams here who are looking into transitioning to liquid rocket engines. This is such an awesome feature of the Launch Canada community, the way that teams are so generous with sharing their knowledge with each other and helping other teams to succeed. So our next presenter is Kefren Gould from the Avionics Division of University of Victoria Rocketry. And Kefren is going to tell us about the 13 sensor data acquisition system of their rocket, named after the elven sword welded by Aragorn, the Anduril 3. Welcome. Where is Kefren?
Just setting up the live stream. You want me to yell to the students out there?
Yes, I do.
Kefren's just setting up the live stream.
Okay.
Hey there, Rocketeers out in the arena. Our rockets are only as good as what we can quantify about them. Some of our biggest challenge is data collection and understanding what the heck that data means. So come on down to our next talk at the stage, all about data acquisition systems.
Hello, hello, test, test. Okay, I guess I'll get started. Hello, everyone. I'm Kefren. I was the avionics co-lead for UVic rocketry for our Anduril 3 rocket that we're flying this year. And the main project that I worked on was our data acquisition system. So I'll get right into it. Yeah, so what I'd like to talk about today is starting off with like our motivation for the project, and then I'll get into a background on instrumentation that was relevant to the data acquisition system that we designed, some challenges that we faced in previous years, and then I'll get into how we decided sensor placement, the electrical design, how we integrated the sensors, the lessons we learned, and then I'll have a period for questions. Okay, so our main motivation for this project was to basically gather empirical data that we could use to validate our simulations. So like pretty much every team, we do pretty significant FEA and CFD modeling of our rocket. And for these types of analyses, it's important to do to have some empirical data that you can actually validate your simulations with, because you can get inaccurate results with these methods. And just as a team, we don't have very much empirical data from past flights that we can actually use for this. So this year, we wanted to basically dedicate our rocket to gathering as much data as possible, so that in future years when we go and do our analysis, we have some data from past flights that we can use to just cross-validate them. And so we focused on mainly strain and pressure, but we also have a suite of temperature sensors that are used for performing temperature calibration for the strain gauges, which I'll get into. Okay, so getting into a bit of a background on the different instrumentation. We have two types of pressure sensors on this year's rocket. One of them is a pitot tube, and so basically the principle of operation of a pitot tube is that you take two pressure measurements, you get a total pressure and a static pressure, and then you can subtract the two to get your dynamic pressure, which is related to your airspeed. And then in addition to the pitot tube, we have three static pressure ports, and so these are to basically allow us to perform this calibration procedure called FADS, flush air data system. And basically what this calibration procedure lets you do is get your 4 air data parameters that let you completely describe the aerodynamic state of your rocket. So that's Mach number, angle of attack, your angle of side slip, and then the static pressure. So yeah, the transducers that we used were all MEMS, piezoresistive, solid state transducers, which you can see sort of in the diagram on the bottom there. You basically have conductive wiring connected to a diaphragm, and as the diaphragm contracts and expands, the resistance of that wiring changes, and you can amplify that and use that to detect pressure. And this is just a bit more of a background on the FADS system that we were targeting to use as a calibration procedure. Basically, your pressure readings are a function of your 4 state parameters, in addition to some other known parameters. So yeah, phi and lambda are just the positions of your pressure ports, and then gamma and epsilon are related to temperature and basically a non-zero angle of attack. And then the eta is just an error term. Yeah, this was our goal was to kind of use this calibration procedure, but even with this system, getting accurate measurements of supersonic flight. So our max speed that we're targeting this year is Mach 1.7, and even in the papers, that basically what you end up seeing is that you can get like convergence issues when you go supersonic, and so even if you can get accurate data, there's often a lot of post-processing that you need to do. And so basically, the pressure system this year is just designed as sort of a proof of concept, see if we can get data, see what we can do with the data. And it's just sort of important to note that this isn't really, if you're really looking to do accurate pressure measurement of supersonic flight, you need a lot of resources, and it is really, really tricky. So yeah, just take that into account. And then, okay, so the next type of sensor that we have on the rocket are strain gauges, specifically bonded wire strain gauges. And so just a bit of background on strain. It's a unitless quantity that measures the deformation of your structure. And so typical units are in microstrain, so that's micrometers per meter. And when you're selecting a strain gauge, there's a lot of factors to consider. There's the carrier material and the grid alloy. So if you look at the table on the bottom there, it gives you different combinations of carrier material and grid alloy that are typically used, and that just affects the actual range of strain that your gauge can properly measure. And so, yeah, depending on the grid material and the carrier material that you use, your strain gauge will be able to either deform more or less, which our rocket this year is carbon fiber. So we selected a strain range of 2% for our strain gauges this year. So in addition to the carrier material and the grid alloy, you also have the gauge factor parameter, and that's basically how sensitive your gauge is to actual deformation. Some gauges will change their resistance more in response to deformation and some less, and that's just quantified by the gauge factor. Then there's the excitation circuit. So that's how you're actually basically applying a current or a voltage to your sensor that you can basically read with your measurement device. There's a lot of different things you can do. We focused on the quarter Wheatstone bridge, and the figure in the slide there is a 3-wire configuration. And what's nice about a 3-wire bridge configuration is that the resistance of your lead wires is canceled out when you go to measure the voltage. So variations in how long your lead wires are, temperature effects on your lead wires are basically eliminated by using this 3-wire method. And then some typical problems that you can encounter with strain gauges are resistance tolerance. So you want to select a gauge that has a low tolerance because basically any tolerance in the actual gauge's resistance will show up as error if you don't calibrate it. And then temperature sensitivity. So this one is a bit more of a problem. The gauge itself is actually sensitive to temperature changes, and so depending on what temperature you're recording strain in, that will actually show up as basically strain in your measurements, which you don't want. So you have to be careful about how you're designing your system so that you take that into account. And so this is the calibration procedure that we designed our system around for the strain gauges. It's called the Skopinski method. Basically, you get, basically each strain reading that you get is described by a function of your 3 principal loads, so your shear, your moment, and then your torque. And you have coefficients that basically, it's just a linear relationship. And so you can basically express the 3 loads just in terms of shear if you know the position of each gauge, which is the second equation there. And then what you get in the end is a system of linear equations, which is n by m. So you have n gauges, and you apply m calibration loads. And typically, you have more gauges than calibration loads, and that makes the system overdefined. And so then you can use this least squares linear regression to solve for your beta coefficients that relate the flight loads to your strain. And what you're minimizing in the least squares is the error between the shear parameters that your model is giving and the actual loads that you applied during your calibration procedure. Okay, and then lastly is temperature sensing. So for this year, we considered thermocouples and RTDs as temperature sensors. And so thermocouples operate through the Seebeck effect. It's basically where if you have dissimilar metals, you get a small voltage that's generated across them, which is a function of temperature. And one of the benefits of a thermocouple is that it has a very short time constant, so it responds very quickly to temperature changes. But one of the major problems with it is that you need a good zero temperature reference junction. So you can see in the figure there, you have these big yellow blocky terminals. Those have integrated circuit semiconductors in them, which basically synthetically give you a 0 degree reference. And so basically the judgment call that we made was that trying to integrate this into, a rocket that's 4 or 5 inches inner diameter was going to be really hard. So that's why we moved to the RTD, the resistance temperature detector. This sensor operates just as a variable resistor. It's a conductor wound around a ceramic. And for metals, resistivity increases with temperature. And so basically that lets you measure the temperature with the RTD. And you have this empirically derived equation called the Callendar-Van Dusen equation that you can solve to relate the resistance of your RTD to the actual temperature of the surface of your fuselage. So yeah, an image of an RTD is just shown on the bottom there. That's the Callendar-Van Dusen equation. Okay, so getting into some of the challenges that we faced in past attempts at, this was specifically for strain, but for our Xenia 1 rocket, which we flew, I think, 4 years ago now, we tried a system where we had a single PCB basically bonded fastened into a bulkhead, and we had basically just a circle of gauges applied around the fuselage. For this attempt, we actually tried to infuse the gauges into the fuselage layup. On the electrical side, we used HX711 strain gauge amplifiers, and we used a half Wheatstone bridge, which is one of the benefits is that it actually eliminates the temperature effects on your strain gauges. But one of the main issues that we had with this was that the gauge wires would break basically when we tried to, during like the process of putting them into the carbon fiber fuselage during the layup. And so unfortunately, we weren't able to complete this project due to that. But this year, we tried a bit of a different approach. And so starting off with how we decided sensor placement. Basically, our current simulations of flight loading basically guided the sensor placement and the specifications that we selected for our sensors. So we had a simulated nose cone pressure gradient, which is shown in the figure on the top there. And we decided that with 4 ports, we'd get a good linear interpolation basically over the entire nose cone. So you can see the placement locations in the figure there, and that's just basically axial distance from the nose cone tip. So we had our pitot tube that's basically right at the tip, which isn't shown, and then the green dots there just show how far down the nose cone that we placed each port. And then, so we had 3 static ports. The transducer for these was the APB2 by Honeywell. It has more than a sufficient operational range for the temperature or for the pressure that we simulated, and then it gives you a 12-bit digital SPI ADC output. So not much is needed in terms of integration. You already have the data is digitized. You can just read it over a SPI input. And then for the pitot tube, we selected a differential transducer, again from Honeywell, that operates pretty similar to the static ports. Okay, so getting into the strain and temperature sensors, on the rocket we placed 9 strain gauge rosettes. You can see in the orange box there how the sensors were placed. In this case, the CAD doesn't actually match what we implemented. We didn't place the lower ring of strain gauges just due to time constraints, which I'll get into as some of our lessons learned. But yeah, like I said before, the operational range for the gauges that we used was plus or minus 2%, which is basically just 2 centimeters per meter of strain. And then they have a nominal resistance of 350 ohms, and then that's just the grid size. And then for temperature, we used a platinum 100 ohm RTD with a pretty low self-heating constant. And yeah, our main focus with this is to basically use it to derive calibration factors to eliminate the temperature effects that basically hamper your strain readings. And so, yeah, I talked about the top figure there. The bottom one shows how we laid out the sensors in the nose cone. So the red box is basically what we call our nose cone avionics bay. It has our COTS telemetry solution, and this year the pitot tube transducer. And so that's just screwed into the nose cone tip. And we have hypodermic tubing that connects from the pitot tube, which is basically slotted directly through the nose cone. And yeah, hypodermic tubing to route the pressure to the actual transducer on the nose cone avionics bay. And then the green box shows an example of a pressure port that we have in the nose cone. And again, we used hypodermic tubing to basically connect the port to our sensors, which are just bonded directly below the port. And then our data acquisition module, which I'll get into, is shown in the pink box there, and it's just bonded to the nose cone. Okay, so getting into the electrical design. So we focused on, instead of just a bulkhead design like in Xenia 1, we switched to a distributed design. So we placed 9 DAC PCBs which share a common CAN bus in the fuselage. And then we placed one of these data acquisition modules in the nose cone to gather data from the pressure sensors. And there's some benefits to doing this. So for the analog sensors, like the strain and temperature sensors, you want to make your analog wiring as short as possible. The longer it is, the more your lead wires affect your measurements. So by designing a distributed system, you can basically, you have a lot more flexibility with where you can place your data acquisition modules. You can place them basically right beside your sensor, and so this lets you get more accurate readings. Another advantage is that it mitigates difficulties with connecting many wires to a single point. So if you have a single data acquisition modules, what you can usually get is you have all your sensors placed throughout your rocket, and you have to basically figure out how to route all your wires to your one module. And so in the past, we've had issues, just basically integration issues with trying to get this huge chunk of wires to one spot on a rocket. So by going with a distributed system with a CAN bus, we can basically just tap off the CAN bus wherever we want and get data which we record with our flight computer over CAN. But some of the disadvantages, so what we discovered with this was that hardware manufacturing, and when we got into actually bonding the sensors, it was very, very labor intensive and very time consuming. So it takes a lot of time to manufacture these 9 data acquisition PCBs, which were custom done. And then when you actually need to bond them, bond the sensors, connect the wires, it just takes a lot of time. And then it also occupies a lot of space. So placing these 9 modules, which we placed in the fuselage, all the wires, basically, it makes, it's hard to find space when you have that many modules. For the digital circuits on the data acquisition module, we used a STM32 G4 microcontroller. We're pretty fond of STM32 at UVic Rocketry. That's typically what we go with. And then the G4 just has all the peripherals that we need, SPI, and then it has a CAN peripheral for our CAN bus. You can run it at pretty high clock speeds, 170 megahertz. This is the first time that we've sort of gathered data at this scale, so we weren't too sure on the computational requirements, so the G4 is definitely more than enough to handle the sampling rates that we selected. We have a CAN transceiver, which is shown in the green box there. A nice thing about the model that we selected is that it takes 3.3 volts as input. A CAN transceiver actually drives the CAN bus, and so it needs to basically output, I think it's 2.4 volts for CAN high and 1.2 for CAN low, and so sometimes they take really weird supply voltages. But a nice thing about the one that we selected is that it's 3.3 volts, so you can power it with the same supply as your microcontroller, just simplifying the design. And then we have the ADC that we used. It's a 4-channel ADC. You can sample up to 150 kilosamples per second. And yeah, it's 24 bits. And that's what we used to sample the strain inputs for our strain gauges. And then the pressure port inputs are already digitized, and so we just have a connector shown in pink there that we plug the pressure ports into to gather the pressure data. Okay, so that was the digital circuits. Getting into the analog circuits. One of the tools that we used to design the analog circuits for the system was this software called Signal Chain Analyzer that's made by Analog Devices. And you can do noise and error simulations with the software. And so for us, it was a really useful tool to optimize basically our signal chain, so our amplifier, our filter, and then our analog digital converter. And so we simulated a couple different circuits with this software. We considered a differential amplifier for the amplifier stage, and we also considered active low-pass filters instead of passive. And there's some trade-offs when going to an active filter versus a passive filter. An active filter, you can really get a better roll-off, and you have more control over the actual frequency response of your filter. But what we found was that for just a simple low-pass filter that does anti-aliasing, which is a concept from digital signal processing where if basically you have your sampling rate, and basically you want to sample at twice the maximum frequency component in your signal, and so by having an anti-alias low-pass filter, you can select what that maximum frequency component is. And so, yeah, we used a simple 2-pole RC low-pass filter and an instrumentation amplifier, and this provided an optimal balance of noise, air, and cost performance. The amplifier was set to a gain of 60, and then we had a sampling rate of 250 hertz. And then for the instrumentation amplifier, we used the INA 351 from Texas Instruments. And this basically, this instrumentation amplifier is really low cost. It's about between $1 and $2 per amplifier, which is significantly lower than a lot of other options on the market. Some of the trade-offs are that you have a really high offset error with this amplifier, so it introduces pretty significant offset into your readings. But we have a calibration procedure that we run to remove this, and so we don't really feel the effects of the added offset error, and we save a lot of cost by going with this option. And then for the RTD, we sample at once every 2 seconds, gain of 4 with another instrumentation amplifier, and then we just use the internal STM32's 12-bit ADC to sample from the temperature sensors. And this is just a sample output from the Signal Chain Analyzer software. So this is just for total noise as an example. And so the software can actually break down the noise contributions of each stage in your signal chain. So from the amplifier to your ADC. And so you can use this to basically balance out the noise contribution so that you're not spending a huge amount of money on one stage and then getting completely hurt on your noise margin from another stage. And then for the PCB layout, the PCB contains both digital and analog circuitry. So basically the main focus during the layout was to separate the digital and analog routing. So to do this, we use separate power supplies for the analog and digital side. You can see those in the bottom figure there. So the green is the digital, and the blue is the analog. And then we placed all our analog components on the bottom of the board and all the digital components on the top of the board. And so that basically reduces the effects of coupling from the digital communication into your analog measurements, which you obviously don't want, because the more you have coupling into your analog lines, it shows up as just an error in your readings. It shows up as noise. So that's what we did for the PCB layout. And then for sensor integration, we had someone from our Center from Aerospace Research come give us a talk on how to bond strain gauges. And so when you're bonding strain gauges, it's really important that you keep the surfaces that you're preparing with clean. Any residue from your skin or any oils can basically reduce how well strain is transferred from your fuselage to the actual gauge. And so yeah, we basically sanitized the surface with isopropyl, and then we sanded the fuselage with 200 grit sandpaper to prepare the bonding site. And then we used a low viscosity epoxy, just a generic brand epoxy, to basically fasten the gauge onto the fuselage, which you can see in the image on the right. That's after we bonded the data acquisition modules and the strain gauge. And you can see on the left side how we actually set up the gauge to be placed in the fuselage. So we use tape, which is pretty typically done. We basically prepared the gauge rosette on our clean surface, soldered bondable terminals to the gauge wires, and then assembled the connector. And then we placed tape over the actual gauge, and then folded it back onto basically the person that was bonding it, folded it back into their hand, and then that allowed them to basically reach into the fuselage. And then you can see in the image the hard points that we used to bond the modules. We also had an alignment feature, which is basically protruding from under the PCB, and that we basically tried to slide. The person basically tried to slide their hand right up until it was touching that alignment feature, and then placed their hand down, unfolded the tape, and then took their hand out. And by doing that, that basically was sort of a reliable procedure that we found to bond the actual gauges. And then, yeah, to bond the DAC mounts, it was just the standard 5-minute epoxy. And then for the RTD, we used the same epoxy as the strain gauges. This isn't actually optimal at all. So for these temperature sensors, when you're bonding them, you really want to use a thermal epoxy that has a high thermal conductivity. And so that's something in future iterations that we're looking to improve on, is to use the proper epoxy. And then for the pressure ports, we fastened the transducers to the ports with hypodermic tubing. And then the ports were bonded the same way as the gauges with just 5-minute epoxy. And yeah, that's it for sensor integration. And then software. So for the software, we used STM32 CubeMX and VS Code for software design. It was all done in C. A nice thing about CubeMX is it basically just lets you configure all your peripherals and all your inputs through a graphical interface, so you can get it done really quickly. And then because the modules were responsible for recording from a lot of different sensors, we used FreeRTOS as a real-time operating system to organize work into basically concurrent tasks that run in parallel. So you can see some examples from some of the tasks. One of the things that we did, which I think was really good, was for the CAN transceiver, we had a dedicated task for basically managing the actual peripheral. So all the different tasks that actually recorded data from the sensors would basically call this CAN manager task by adding a struct to a queue that the manager task was monitoring. And then the task would basically unpack the messages from the queue one by one, check if the CAN peripheral was ready, and then just transmit them. And that was basically a reliable way to synchronize all the strain reading, RTD reading, and pressure reading tasks so that we're gathering data reliably. Yeah, for sure, yeah. Just getting into some of the lessons learned. Proper strain gauge bonding is costly. So we used generic brand low viscosity epoxy, which we've learned isn't really optimal. You really have to use the manufacturer provided dedicated strain gauge epoxy, which really provides like the lowest bond line, which is what you want for reliable strain readings. The problem is that it's super expensive. So just take that into account if you're looking to do strain readings. And then, yeah, for next iteration, we're definitely going to use thermal epoxy for temperature sensors. And then getting into the actual system integration, we found that the distributed approach for data acquisition was really labor intensive between bonding the gauges, bonding the sensors. It takes a lot of time. And so that's just something to take into account. If you're looking to set up a system that's similar, it's going to take quite a lot of effort. And then, yeah, for the analog circuits, the single chain analyzer software was a really useful tool for optimizing the system. And so some of the next steps for us are to basically perform the calibration procedures that I talked about, so the Skopinski method and then the FADS method, which we're going to do post-flight. And that'll help us basically analyze the data and see if our readings actually make sense. And then for future systems, looking to do further cost optimization, potentially using a cheaper microcontroller with a lower clock rate, less capable. I think this year we used one that was more than enough. So we could definitely save costs there. And then, yeah, just refining our bonding procedure, using the proper epoxy. And yeah, so if there's any questions, I'd be happy to answer them. But that's all I have for the presentation. Thanks for listening. Yeah, thank you.
Thank you, Catherine, and for taking us through your sensor design. That was very, very informative. If anyone has questions for Catherine, you can just find him at the UVic tent over the week. Ariana, can I call you up to try to bring in the students in the other room for our next speaker?
I'd say go ask. Hey there, Rocketeers out in the arena. This one's going out to a lot of the new teams that are starting up, starting to get into simulation work. Maybe you're on a team that's trying to go higher, faster. So you're looking to, the next talk here at the stage is focusing on all of the different software used to simulate a rocket's flight. So please come on down and learn how you can project your trajectory.
Okay, next we have Nadeem Houteem is the aerodynamics team lead for the University of Toronto Aerospace team. And Nadeem is going to tell us about the team's investigation into 3 popular rocketry software packages and their comparative accuracy in flight predictions. So let's welcome Nadeem to the stage and see what they have found.
Hey everyone, I'm Nadeem Houteem. I am the aerodynamics lead of University of Toronto's aerospace team. I've been here for 2 years, and I want to talk about how accurate different rocketry simulation softwares are. I think this is an important topic because no matter what size of team you are, either you're like a high school team developing your first solid rocket or you're developing your 100,000-foot liquid rocket, you need to use the simulation softwares. You need to have an idea of how your rocket's going to perform without actually launching it. And so here we're going to do just that. I'm going to take these three softwares, OpenRocket, ROS-Aero, and RockSim. I'm going to compare the simulations they return to our actual flight data from previous launches, and we're going to see how they hold up. So there you go. This is the overview. I'm going to go introduction. I'll give you an overview of each software, how they work, what the differences between them are. Some key considerations, because we got to make some assumptions. Go through subsonic, supersonic, and then discuss. Here. So this is what I was talking about. The key considerations we're gonna, the key aspects we're gonna consider for each flight is the apogee they reach, the max velocity, how long the flight takes, so the total flight duration, and dispersion analysis, how far the rocket goes. I found that these are probably some of the most important aspects you want to take into consideration when designing a rocket, and so we'll be doing them. First, each software. OpenRocket. This is probably the most popular rocketry simulation software. It's open source, made in Java. It uses the extended Barrowman analytical method to determine your flight. And what the Barrowman method is it is a mathematical model developed in the 60s. It divides your rocket up into some key components, primarily your nose cone, body tubes, fins, and then it performs calculations on each one of the components. It considers the interference between each component, and then combines them all together to end up with the final center of pressure of your rocket. And then with that center of pressure, you can perform different aerodynamic loads, you can see what the stability is, all that good stuff. One main issue with the Barrowman method is that it only works with small angles of attack, and it only works under Mach 0.7. So OpenRocket uses the extended method, which was developed in the 90s, in which you can extend the Barrowman method for even larger angles of attack, making it more applicable for general rocketry use. OpenRocket also performs some level of a Mach correction for flights greater than Mach 1. And we'll see how effective that correction is later in the results stage. Next, we have RockSim. RockSim is considered an alternative to OpenRocket. It's paid, whereas OpenRocket is free. Consequently, because of that, RockSim also uses a modified Barrowman model. This is similar to OpenRocket. However, while OpenRocket's model is open source and known, it's reliant on previous data, RockSim's model is actually proprietary. So no one outside of the company is entirely sure on how it works and how they've modified it to be more accurate. And that's why we do these comparisons. Other than that, it is fairly similar to OpenRocket in all of its features, and it's a good tool to use. There. Finally, we'll be using ROS-Aero. ROS-Aero 2 is fairly different from the other two softwares. It's much more popular in supersonic flight. This does not use the Barrowman equations as its main source of aerodynamic loads. Rather, it uses a combination of the United States Air Force missile DATCOM methods, which are a combination of empirical findings from experiments in wind tunnels and through equations, as well as shock expansion theory to model supersonic flight in a much more accurate manner than the previous two softwares. It also takes into consideration much more, it makes an effort to have much more accurate supersonic methods through the use of Van Dreist boundary layer formations, in which you can take incompressible flow, which you experience at supersonic speeds, and convert them into a workable fluid region next to your walls, your rocket walls. There you go. So before we get into our analysis and the comparisons, we're going to look into some key considerations. First of which, garbage in is garbage out. This is maybe the primary rule of any sort of simulation. Your simulation is only as good as the rules you put into it. And so in this presentation, we have the benefit of hindsight. Everything we're doing is with already existing rockets. We can see what the wind speeds was like at the time. We can see how the rocket was exactly built. And so we didn't have to make any predictions. Obviously, if you're creating a rocket in the future, you don't have this benefit. You're going to have to make some assumptions. Some of them might be wrong, and it's going to affect the quality of your resulting simulation. Also, we have some software-specific limitations. Some of these softwares have capabilities that others do not. For example, ROS Aero does not automatically calculate center of gravity, and so you would have to either manually do that using a CAD or physically weighing the rocket, or you might use one of these other rocketry softwares to do so. It's very common, at least in UTAT, to use OpenRocket to generate the mass and center of gravity for the rocket, and then use that data into ROS Aero and get more accurate simulations. Finally, as we're going to be comparing these simulation methods to actual data, it's important to consider that the actual data isn't necessarily 100% accurate to what really is being experienced by the rocket, since the data is being collected by sensors, and these sensors have their own internal errors. Some of them don't have a high enough sampling rate, some of them might have just some malfunctions. So take that into consideration. Here. First, let's start with subsonic flight. Here. What we will be comparing to is disruption. This is a solid rocket that U of T launched in 2024. It reached an apogee of around 10,000 feet, reached 961 feet per second velocity. It's transonic in that it reached a Mach number of 0.85, but the majority of the flight is in a subsonic region. And then it landed 875 feet away from the launch pad. All of this data was collected by a stratologger, and so that is where the source of errors come from, if there are any. Now, comparing this to the data from our simulation softwares, here. First, you can see that most of the softwares were able to get a pretty accurate reading compared to the actual flight. In apogee, ROS Aero was the closest, but everything else wasn't too far off. In maximum velocity, they were all pretty accurate. We'll get more into the quantitative results later. Flight time, they're all pretty spot on. The only place where they seem to differ pretty greatly from the actual data is with the landing distance. You can see all three rocketry softwares over-predicted how far the rocket would land away from the launch pad, with RockSim actually predicting more than double the actual distance. We'll get into why this may be later, but it is an important thing to consider when you're doing your landing dispersion, although it's always better to over-predict than under-predict. So, yeah. Next, we'll go into supersonic flight. For this, we'll be comparing it to our hybrid rocket. That is Defiance Mark IV. We launched it in 2023, reached an apogee of around 30,000 feet, 29,156, maximum velocity of 1,576 feet per second. That means it's a Mach number of 1.4, so this is well past transonic. This is a supersonic rocket. It landed 875 feet away from the launch site, and for this, the data is being collected by a featherweight GPS. So it might have some differences in how it collects data compared to the stratologger. And here we have different results. You can see that RockSim and OpenRocket both aren't able to predict the apogee as well as ROS Aero for the supersonic flight. It's not as evident on the bar graph due to the high numbers, but both were off by a couple thousand feet. For maximum velocity, they were around the same, in the same ballpark as the real value. For flight time, RockSim and ROS Aero actually under-predicted how long the rocket would be in the air for, while OpenRocket was closer to the real results. And for distance from launch pad at landing, ROS Aero was the only one to get near the real results. RockSim and OpenRocket both underestimating to a greater degree. So let's look at the actual quantitative numbers of these results. I feel like this gives a better idea than the bar graph. You can see highlighted in green which software performed best in each specific category. And so for apogee, ROS Aero performed the best. For max velocity, RockSim. For flight time, it was ROS Aero. And for landing position, it was OpenRocket, although even it over-predicted the landing distance by 30%. This is all for disruption, by the way. But you might notice that there is no clear best choice in terms of software here. Each software has its own pros and cons. It's kind of spread out in between them. Now, why might this be? So it's possible that OpenRocket underestimates the apogee because it assumes a fully turbulent flow over the rocket body. That means that the drag it's assuming is going to be much higher than the real drag the rocket's experiencing, and thus it's going to predict the rocket's going to go lower than it actually will reach. Similarly, RockSim has a more sophisticated surface roughness method, which leads it to having a higher apogee, but still it underestimates the flow as compared to Ross Arrow. Next, we can see that the peak velocity was underestimated by all three softwares. This shows kind of the difference between the ideal thrust curves you get from manufacturers, because this is a solid motor that we bought, compared to what you will really experience by the rocket. This is due to a variety of reasons. You can consider the friction from the rail, from the launch rail, some tip-off perturbations, maybe some wind effects on how the rocket's able to combust. All of which can contribute to your estimations for max velocity being lower than the real values. Finally, we can consider the landing distance and how it was overrepresented by all of three rocketry softwares. This is due to the complex nature of wind and how wind, most likely, is due to the complex nature of wind and how wind changes as you change in altitude. Most of these softwares predict either a consistent wind speed throughout your entire launch altitude, or try to predict what the wind speed is using forecasts, but even then, those forecasts are never fully 100% accurate, even when we're looking in the past. And thus, you end up with these landing distance overestimations of 32% to even 100% in the case of Roxen. Here. Now, moving on to the supersonic rocket, this is Defiance. Here, you can see much more of a clear trend. Ross Arrow seems to be much more accurate than the other two softwares in apogee and max velocity and in landing position, with only flight time being a component where Open Rocket seemed more accurate. And why that might be? Really why that is supersonic flight is a lot more complicated in terms of the mathematical formulas. And so when you're working with Roxim or Open Rocket, they're just using the Berman formulas. They can't predict shocks. They can't predict how the shocks are going to affect the rocket's drag and the rocket's apogee. This then leads to your underpredictions in apogee. Additionally, Ross Arrow has these further corrections for supersonic flow, such as the Van Drijst boundary layer equations, which even further contribute to their accuracy in supersonic flow. Here. So, some key findings we had is that Ross Arrow is most accurate in supersonic flow. Roxim is more accurate than Open Rocket in subsonic regions, even though Open Rocket might be the most popular software to use. What this means for your workflow is we recommend using Open Rocket for your initial estimations, initial predictions of CG and mass when you're first starting out with the rocket, but when you want to further validate the apogee and components of the flight, you might want to switch to Roxim if it's subsonic, or Ross Arrow if it's supersonic. However, all this being said, this is data only being compared to two rockets. Ideally, in a real scientific experiment, you'd want to compare it to a lot more rockets, and you'd want to compare it to a lot more variety of rockets. We'll get different wind speeds and different Mach numbers, maybe different types of rockets, like a liquid rocket, other hybrid rockets, other solid rockets. And because of that, I've included a QR code on the top right of the screen. That will lead to the Excel sheet I used to hold these results. If you're curious and want to contribute to this experiment, you can include some of your own rocket data from your own launches, no matter what the rocket is. And then we can incorporate that into these findings and get a more comprehensive view of how accurate each simulation software is in their own specific cases. That is mainly it for us here. If you have any questions, please feel free to reach out to me. And yeah, thanks for listening.
Okay, many thanks to the UTAD team for doing that study and sharing your results with other teams to benefit from. It is time for lunch, and we will resume here at 1:15 p.m. All right, we're all set to begin our afternoon session. So leading off our student presentations for the afternoon, we have Patrick Zvezdan and Noé Peter. Together, they lead the propulsion team for Oronos Polytechnique. And Patrick and Noé are going to tell us about the development and testing of Pegasus, Oronos' first liquid rocket engine. Please welcome them both to the stage.
So, hi everyone. So, my name is Noé Peter, and I'm with Patrick Zvezdan, and we're the two co-leads of the propulsion department of Oronos Polytechnique. And today we'll present you our technology development challenge, which is the Pegasus SRAD first liquid engine of Oronos. So, for the plan of the presentations, we'll start with the Oronos overview of the team. We'll continue with the context and objectives of this project, the subsystem overview, the testing that we did this year, and the budget and the cost breakdown of what we did of the project. So Oronos is a team that has a lot of history in hybrid propulsion and hybrid rockets. So we won 3 times at the Spaceport America Cup in the 10K SRAD hybrid categories. And in 2025, last year, we went to far out to launch our 30K SRAD hybrid. And this year we're launching our hybrid 2-stage at 35K. So it's new for us to enter the liquid propulsion category, and so the goal is to familiarize ourselves with liquid propulsion. So the structure of Oronos is separated in 3 parts. First, you have the administration with the team leads and the treasurer. Then you have the department's lead, which is separated in 5 categories: aerostructure, avionics, communications, payload, and propulsion. And then you have the team members who are the people that are actually doing the jobs. Oronos is also participating in non-technological activities, such like Eureka Festival, Polytechnique, Aero Montreal events, Cosmonaut Spring Break, and Adri Gala Prix of Innovations. Also this year, we organize a rocketry conference at Polytechnique Montreal, and one of the teams here at Launch Canada were there. So for the project, it's a SRAD liquid N-class that runs with fuel, which is isopropyl alcohol at 850 psi, and it's pressurized with nitrogen. Also for the oxidizer, we use nitrous oxide at 750 psi. And as I said before, it's the first liquid engine of Oronos. So for the context and objectives, the stakeholders' motivation, Oronos as an organization, it's to develop the first liquid expertise. Also for Oronos, it's to gain visibility through more ambitious projects. And also for the team members, it's to develop key skills to integrate into growing launch industry in Canada. Also for Polytechnique Montreal, it's to have a high-level rocketry team with expertise in the 3 major chemical propulsion categories. For the technology importance, we would like to address the growing demand for Canadian launch capabilities by doing this project, liquid propulsion. Also, we want to create a base for bipropellant research and development programs within Oronos. So this will lead to more research and development projects. So as I said before, it's a research and development project oriented, and the goal is to develop liquid propulsion expertise, and the market opportunities will be explored with later programs. So for the project summary, we start the project at the end of summer 2024. We finished the design with a CDR in 2025, and we're manufacturing and testing this year the motor, and we will aim to a launch if performance are nominals in 2027. So this year, for the technology development category, we will aim for full duration hot fire test to validate the propulsion system. We wish to achieve a performance of 16 kilonewtons seconds, and we want to train the next generations of members. We will improve the motor and launch in liquid rocket in the coming years.
So for the system overview, we'll start with how we size the engine. So to size the engine, we have an in-house simulation script, which is based on Rocket CA that solves the mass conservation equations and the heat transfer equations in 1D. And we use this script to have a sensitivity analysis for all our performance parameters. So here, for example, you have thrust, oxidizer mass flows, and then combustion chamber versus nozzle float area. So we've had a couple rounds of iterations on that to get to the final sizing of the combustion chamber. And here are the overall dimensions we arrived to for the combustion chamber. I'll leave them out here for a second if you guys want to look at them. And if you have some questions about them, you can just come back to them later, because it's not much to say, just numbers. If you know about them, you know about them. If you don't, you don't. Same thing again here, except I'll just say a few interesting ones. So our mean thrust is around 1900 newtons. Max thrust expected to be 2000 newtons. We have a slight OF shift, as you can see, because our nitrous tank because our nitrous tank is blow down. And that's about that for that slide. Again, if you have questions about those numbers, you could ask them after. Here is one of the outputs of our simulation script. So you can see that the thrust is slowly descending due to the nitrous blowdown, and you see the IPA flow rate is constant. And again, the nitrous oxide flow rate descends due to the blowdown behavior. As for the combustion chamber envelope, for those familiar with our previous hybrid rocket engines, this is basically a copy-paste of that whole design philosophy, except with a redesign at the manifold and injector. So we use a threaded assembly on both sides of the retaining ring with a phenolic fiberglass liner, a nozzle which materials may shift. Materials will change depending on the context. We will be testing our flight. The motor head, again, very similar in geometry to what we've had, and the injector and manifold. Not to go into detail of the flow path. So we opted for an axial injection for the nitrous oxide with a shower head injector. The IPA is purely radial with a slight tangential component for better mixing. And here is our injector in more detail. So here you can clearly see there's the axial flow on the left-hand side, and you can see the IPA with the slight swirl given to it. And there's also the machine injector itself, which is in our engine right now assembled over there. And we also inject in a non-premix configuration. As for the liner, we just have your standard SRAD fiberglass phenolic liner. If you're familiar with them, you know how they work. You lay them up, and at the end of a burn, they usually toast. And here are just a few chamber dimensions for those curious. Nothing too fancy about that. As for the nozzle, so the nozzle is a pretty interesting story. We initially wanted to have it in aluminum, and we tried some metal bonding to it to see if it would survive. We had done some research and some thermal simulations on it, and we thought it would work. And as Noe will show you later on in the testing overview, it did not work. So for the test purposes, we switched back to stainless steel, and we'll probably stick to graphite for the launch, if there's a launch or when there's a launch. As for the retaining rings, again, just 66:1 machined aluminum manifold also. The motor head was also the same design process as the nozzle. We thought we could get it to be aluminum for mass saving and metal coated to survive the heat of a combustion chamber. Again, it did not work. Noe will show you pictures of what both of these pieces look like after the burn. And we also switched it again to stainless steel. As for our fluids control architecture, so this engine's goal, again, is to get a liquid engine firing, not necessarily to get it to fly. So we went for as much of a COTS setup as possible. We have a 3-tank configuration with all our tank and plumbing as COTS, and only the combustion chamber of this setup is RAD. So as you can see, tank support 2 has our fuel tank and our propellant tank, and that's our whole propellant assembly. And then tank support 1 is our nitrous oxide assembly, which is, again, just a blow-down configuration. Then on the fixed plate, we have our main feed line and our fill line for our nitrous oxide. Again, yep, nothing much to say about that. As for propellant tanks, as I said, we're both COTS. The nitrous oxide tank flew actually in the spaceport of 2023. As for the IPA tanks, well, they're COTS COPVs, which were hydro-tested to 780 to 200 psi. Well, why that's important is because we for our operations, we need to be able to operate next to the setup while it's pressurized, and according to the launch can DTEG, you need to have a factor of safety of 4 on your tanks. So, yeah. Now for testing overview with Noé.
So for the testing overview, these are the tests that we did. So we started the testing campaign in May because we were occupied with our hybrid engine the rest of the year. So we started with a tank hydrostatic test. Then we did a chamber hydrostatic test. We also started with cold flows. We did 3 cold flows, and then we went for first short duration hot fire that we will go more in details later. And the test number 2 is this week at Launch Canada that we will be aiming for the long duration. So for the cold flow, we used water plus CO2. So the first cold flow, the issues that we had, first it was leak in the tank fittings. Then we had also issues with the filling process of the water that were non-nominal. And we had two pressure transducers that had anomal data. So here's the video of the first. Then we assessed the problems that we had at the first cold flow, and we did another cold flow, and we had the pre-injection pressure of CO2 at around 547 psi, and the pre-injection pressure of the water at 288 psi. But then we were a little bit concerned because the expected chamber pressure for static fire that we were running in the simulation was 370 psi. So we were expecting, or we were wondering about the backflow of the IPA in the line. So this is the second cold flow that we did. Wondering if we didn't have a low pre-injection pressure of the water because of this leak. So we did the third cold flow, but without the CO2, so just the water line. And we had a pre-injection pressure of 122 psi, which was even more concerning. So we came to the conclusion that the pre-injection pressure of the IPA line was dependent of the chamber pressure. So we move on to the static fire. So these are the data of the static fire. So at the top you have the thrust, then you have the mass, and then you have the tank pressure of nitrous oxide, tank pressure of IPA, tank pressure of nitrogen, and the pre-injection pressure of both lines. You have also the performance sense that we have. So we almost reached 3 kilonewtons, but we were expecting 2 kilonewtons, and the pre-injection pressure were almost nominal. However, we lost the chamber pressure, so we didn't have data on it. So here is the short duration static fire that we did 1 month ago. As you can see, the first seconds was correct, but the second seconds we had a burn shoe in the nozzle and in other parts. So as you can see, the nozzle is completely destroyed. The motor head also. The liner cracked and was damaged, and also the injector was damaged. So the change that we are doing for Launch Canada and the static fire that we are doing this year is that we changed the material of the motor head and nozzle to go from aluminum to steel. And we tripled the thickness of the liner, and also the injector, we redesigned it to prevent the flame circulation behind the edges, to prevent an attachment of the flame, and to attack the injector. So we added some chanfreins to the corner of the injectors. So now if you look at the cost breakdown, here you have the consumables, so COT tank that we use for cold flows, NOx tank, IPA tank. Also, you have the motor hardware, so it costs us about 4K of hardware to machine and to have the pieces. And for the fluid system, we're lucky to have Switchlog as a sponsor. So main of the fluid system were sponsored by Switchlog. So thank you for listening. This is the sponsors that we have. And if you have any question, we'll ready for it. And we can also go to our booth if you're interested more in the project.
So, yeah, our combustion efficiency is basically an educated guess based on past motor performance. For example, on our hybrid engine, we initially guessed our combustion efficiency to be about 90%, which led us to having to redesign the nozzle because it did not have the performance we wanted. I think it's closer to between 70 and 80 what we have in the chamber. So yeah, it's an educated guess based on past testing history. Whereas, could you say again? I did not hear that.
Did you iterate on the combination of injectors before you landed on a specific combination?
We were quite lucky that it worked the first try. I'm genuinely, we just got super lucky on that. We didn't have to iterate. We had the performance we wanted on our first cold flow, so mass flow wise, yeah.
Thank you. Oh, thanks again, Patrick and Noe. That was fantastic. Again, it's so helpful when teams share both their successes and their failures when trying new things. Everyone can learn from that. Our next presentation, Ariana, do you want to come up and do your thing?
Hey there, Rocketeers out in the arena. Once again, we're ready to invite you down to the stage for our next talk. This one's being given by Western Rocketry, and they're going to be presenting their spin casting method. This one goes out to all you hybrid lovers. Come on down.
actually a little bit ahead of schedule. Our next talk is at 1:45, so we'll start at that point. Okay, here we go. Our next presentation is from Western Engineering Rocketry. We have Chief Engineer Dylan Peters and the team's advisor and product engineer Ethan Ackerman. And Dylan and Ethan are going to tell us about their solution for the consistent manufacturing of defect-free hybrid engine fuel grains. Please welcome Dylan and Ethan. Sorry.
Thank you. All right. Well, hey there, guys. We're from Western in London, Ontario, and as part of our final year project, we decided to tie it in with the rocketry team. We're from We Rocketry, who has never once built a hybrid engine before. So over the last couple of years, we've decided to make it somewhat of a goal that we'd want to start building systems that would help us make a hybrid engine in a kind of a creative, different way. Our school doesn't have an aerospace program, but we have a lot of people interested in it, and it's been a really fun experience overall. Cool. Wanna go with this?
Yep. So what we're doing, our kind of goal here is to be able to replicate a system for creating consistent defect-free fuel grains. We're doing this through a centrifugal casting system. Later on, we'll show you the benefits that it has over a pour casting system.
Yeah, so we've been a rocketry team since 2016. Our first launch was at Spaceport America Cup in 2022, and we've been coming to Timmins now for a couple of years. We had our launch last year, and up until now, we've always been a COTS solid team, and we just wanted to make some steps towards that. One of the things we identified as kind of something we could work on, automate, and really try and hone in on was the manufacturing of fuel grains. So we had our capstone team here. I'm Dylan.
I'm Ethan.
And our other two members are a lot more employed than us, so they are not here right now. But we decided to get together and target this as a project. We wanted to make fuel grains that were capable of being cast directly into the liners of commercial motor casings. So that way, you know, in whatever case we decided to create our own custom casing on the team, or if we decided to integrate with a Cesaroni or Aerotech motor, it'd be able to work no matter what. We wanted it to be safe because this thing has to be able to operate continuously over a long period of time while it cools, such that it doesn't crack. We also wanted it to be able to install and remove easily with no issues. And finally, we wanted to make sure these grains had no defects. So the main material that we used here was wax, paraffin wax. We used paraffin wax because it is easy to work with, it's readily available, it's something that isn't an explosion hazard when you're trying to work with it in the little machine shop out beside the Formula car. And it also has some very advantageous material properties of its own, particularly in its regression rate and combustibility trade-offs. It's something that will also allow us to eventually add in some fuel additives like aluminum powder or even some kind of polymers.
So when looking at prior applications of systems such as these, we found almost nothing. This is not something that's really done anywhere that doesn't require an NDA. So we didn't have a lot to go off, but that also led us to have a lot of freedom in our choices. The grain that we're using for our fuel is a Bates grain, which is a fuel grain with a hollow cylindrical inner diameter. So when looking at what type of concepts to select, we had narrowed it down to 4. Number 1 was what we ended up going with, which is our end-supported horizontal spin casting system. So you'll see later on that our fuel mold is attached at either end and rotating around its axis. Our drive system will make it spin, and this results in a very evenly distributed force. Our second option was to put it onto rollers, and frankly, this is not something that we thought would be very safe. There was just a lot of risk involved. We didn't want it to fly out. Our third option was very similar to our first. Instead, it would be oriented vertically, We thought about doing this. It would be very efficient for space. However, it would create coning, which is shown in the picture, just due to gravity. And our fourth was traditional forecasting, which is consistent, it's reliable, but it allows for more room for defects and air bubbles, which we don't want because they can cause explosions. Not good.
This stuff is boring. If you've ever got your engineering degree, you've used these QFDs before, you use them, you hand them into your profs, and you call it a day. But what we do get out of it is a good actual way of having documentation to show why we selected something. Now, I can tell you why we did, and this is way more fun. If you've ever worked with anything that has to mold and cool, major problems that you'll see all the time are things like shrinkage, are things like cracking. And these come due to just the dissimilar materials, the changes in temperature, rates of cooling. When you're trying to target not only an outer diameter that's smooth, but an inner diameter that has the shape that you want in order to be able to direct your flame front in your engine properly, this is all things that you have to consider. Another thing that we wanted to make sure we were tracking was avoiding what we call additive sedimentation. This is so that when we go to eventually add in something like aluminum powder to have it a bit more combustibility, that we've already designed the system such that it has the controls that it can properly cast without issue. No one cares about that, but what we do care about is the design process itself.
All right, so after we selected our horizontal spin caster idea, we had a lot of ways to go about it, again, because there's not really a reference for it. And what we ended up with was something similar to what is shown here. This is a pretty detailed drawing of what we ended up with. There's a second slide of it as well. Took a lot of time and effort to get to this stage.
We also decided that we wanted this to be a programmable, adaptable, integrated system because both of us are now graduated and we will be leaving our team. So we wanted to leave the team with something that could produce them fuel grains for the team, be adapted into the future, and be easy to use. So it has different sensors within the system, as well as an ability to actually pre-calculate how long the fuel cycle should be and operate at that RPM with the proper ramp up and ramp down rates and safety features.
So for the construction of our model, we started off with building the structure. That was just the natural start to things. We made it almost entirely out of aluminum extrude and then aluminum angles and plates.
Aluminum extrude is God's gift to man.
Yes, it saved our entire project. It was beautiful, thank goodness. And eventually you'll see here we were able to integrate our power systems, our fuel systems, everything. Honestly, almost to the T with our CAD drawings, which was beautiful.
At this point, we began our just basic electrical prototype testing. You can see there, breadboard, standard system. This is a belt drive system here, just in order to create a bit more of our torque it up for speed instead of for torque. Of course, we had our validation plan because not only do we want this to be a system that produces good fuel grains, we want it to be a robust system on its own. So we were not only looking at things like the grains produced, but also just how it functions as an integrated system. And we tested this at many different stages. You can even see down in the bottom left corner, I believe, a pour casting test that Ethan performed, which was meant to be used as a control to show that there is shrinkage and even a little bit of pooling and coning in traditional methods without pressure that you don't get with a spin casting system that runs automatically. Also, you can see the start of what was a 3D printed model that we began to make.
Other parts of our validation plan that we wanted to test, just with this mandrel being spinning at hundreds, if not thousands of RPMs at a time, we wanted to make sure if anything went wrong, it would not go wrong in our face. So one of the things we made sure to do was just test our guard, and what that ended up being was myself grabbing heavier and heavier objects and dropping them on the guard from height. After some calculations that were done by one of our other team members, we determined that even at our highest speed, with a full load, it wouldn't explode the guarding in our face. Very, very good to know. Honestly, very comforting.
Also, we did full system dry runs that exceeded the maximum amount of time that we expected the system to run for to make sure that it would be able to operate safely, it wouldn't break, yada, yada. Okay, long story short, it totally did break. We snapped one of the bands on our motors almost immediately, and that is not good. So we went back to the drawing board. We switched to different, stronger belts in order to drive our motor. And we continue to operate like that. This is why our safety testing was pretty thorough. Now, you can see here was the full system test. This is the meat and potatoes of our project, and this is actually how we would intend for it to be used. If you see the top view here, from the left onwards, there's our system structure, guarding, your standard stuff. At either end, we have bearing supports. So at the one end, you can see tape off. That is such that you can rotate the system up and pour in molten wax that has been melted to whatever temperature it requires. As you move in, you can see some custom machine bulkheads that can actually integrate directly with COTS motor casings. So if you were to install a liner into that casing, you would be able to effectively pour these to the exact spots you want, cap them to the sides, and have your fuel grain cast as you wish. Also, in this case, we ended up pouring directly in with the aluminum. That's because we're able to just melt the wax back out and test with it again afterwards. At the very far right of our system, you can see our motor drive, some standard stuff, and our whole electrical layout.
So we did end up doing a full system test with a pour, as Dylan mentioned, and it exceeded our expectations. It prevented the shrinkage outside, just due to the centrifugal force, and it created a hollow inner geometry as we wanted it to. It did create some flashing near the ends, but that is something that is easily fixable just by cutting it out.
Yeah. So as a whole, we think that there were certainly some technical challenges encountered in the project, but we feel like this is the sort of thing that would be an interesting way to have adaptable and repeatable casting of simple, basic fuel grains that you can put additives in and extend to further projects. With further testing, you could experiment with different materials to slide in and out and then trim that flashing at the end, and even cast with short scale Bates grains. Now, one thing that we began to work on that is ongoing in testing were those 3D printed parts I was alluding to earlier. So we've started to work with polypropylene, which has some warping issues, but that would allow for casting of this wax material with whatever additives you'd like within a fully adaptable 3D printable model at the scale of a Bates grain. So you'd be able to cast 6 of these in a row if you wanted to, say, do a 6G motor, and then stack them in at the length of whatever casing you'd like.
Yep. So one thing that we did run into was cost challenges. This being a final year project, we didn't have an unlimited budget. Initially, we were given about $1,600 to work with, so in the grand scheme of things, not a lot. We ended up going a little over that, but through this, we were able to overcome this challenge just by doing some of the things ourselves, such as machining and manufacturing. It was not easy. It was definitely an arduous process over the course of about 8 months, but it can be done under a tight budget.
Yeah. Overall takeaways, on the one side, there's project management lessons, which for everyone's learned here for other things, but most of all, it was that a project like this, whether or not it's something that's within your wheelhouse, you should never be afraid to go and find people who are interested in the same topics. We even reached out to some researchers in, say, Milan or otherwise in Canada, just to see what it was that they were making progress with, what they had challenges regarding, and it helped us quite a bit. Something else that I'm sure a lot of you have encountered too is your shop supervisors, or your buddy who works at the machine shop down the road. They might know a lot more than you do about a lot of things, and there's a lot of value in just going and taking your proposal for a design to them and letting them rip it apart and seeing what you can get out of there. So you can make something that anyone can make and anyone can use. So that's all from us. We'd welcome any questions, but thanks for listening. Yeah, so that's totally right. What we started to experiment with and what we'd have to do further work on would basically be adding in these additive particles throughout the cycle such that, so our system can actually be turned on its side vertically. The test horizontal were for convenience. Adding it throughout the cycle such that you kind of take advantage of the cooling of wax, because wax does get, thicker is the wrong word, but it begins to solidify. And we've been trying to find when the right time is, which you can calculate all the heat transfer, right? Some basic third-year stuff, and see if we can get it such that it'll spread out and kind of freeze in that position. We bought basically these little the smallest beads we possibly could in varying colors just off Amazon. And so we've just been trying to spin those and pour them. And we've been having some success. Of course, you wouldn't ever get, the perfect mixing that you'd have like an industrial mixer, but we feel like we could definitely hone in a bit further, and we're hopeful that it'll give us good results.
One thing I definitely think we would have improved upon is just, we probably would have had access to more standardized parts. A lot of the manufacturing we did was in-house. So we saved a lot of money on that. It was a very good experience, but if we're looking to make a more refined system with a higher budget, I think that's something that we would look at for sure.
I would also really, really love to extend this to the spin casting of phenolic liners. And if I had more funding, I absolutely would have, again, within the confines of a capstone project, you have certain amounts of funding. But if this were to be extended now by the team in the next year, I would love to see spin casting of a liner layer with the same system, and then spin casting of a fuel layer onto that liner.
So we kind of have a base temperature that we pour it in at, and we've done heat transfer calculations to kind of just, based on an ambient temperature around it, see how long roughly it'll cool at. So I believe we melt the wax to about 90 degrees Celsius before pouring. And from there, we have the option to cool it with a fan or just leave it up to ambient temperature.
And a future system we have the space on that left-hand side of our system such that we might even be able to heat it up and then directly have it pour in with further funding. Oh, sorry. No, it's fine. You want us to come up here? Yeah.
So as far as the shrinkage goes, we're okay with it shrinking internally, so long as the outer geometry remains the same. Just the centrifugal force will definitely make sure of that. And then, what was the second one?
How do you check for defects and cracks?
And then, as far as checking for defects and cracks, just during our testing, just because it's easily repeatable by melting the wax back down, we would just take our fuel grains, take them out, and then cut them. Just to honestly get a good idea of where everything's at.
Thank you. Cool. All right. Thank you, everybody.
Okay, thank you, Dylan and Ethan. That was great, and great questions. There's obviously a lot of interest in your work, so thank you for sharing that with us. Our next talk is by Arbalest Rocketry. We're going to take a very short break and resume at 2:15.
be covering today? Well, we'll be covering, we'll walk through the development process and how we develop the system. I'll be discussing why active control is useful for and why conventional rocket simulations don't work. From there, I'll cover the fundamentals of rocket aerodynamics and how these forces and moments can be modeled in a full 6 degree of freedom simulation. Then I'll talk about how our guidance and control systems work, including the control architecture used on our rocket, and I'll end with our Blue Jay test campaign, which was our series of rockets that we used to fly and test our control system. Okay, so just some background. This year, we flew 9 flights testing out our rockets. We worked on our, our minimum diameter rockets this year, and active control really stood out to us because it combines aerodynamics, simulations, electronics, mechanical design. It combines all of our sub-teams together into a new project. So why do we really want to do roll control? Well, roll control is super important because an uncontrolled rocket can spin out of control, and this is called roll pitch coupling, where the roll rate of your rocket matches the frequency that your rocket stabilizes. And this rotation, it can continuously rotate around the vehicle, and it can do like a corkscrew motion, and this can cause shredding, like the photo in the middle. Limiting roll also improves the video quality. That's why we had spin cans in previous years, was to keep the rocket from rolling. And if the rocket spins multiple times in 1 second, it can make it really difficult to interpret what's going on. Okay. Conventional rocket simulation software like OpenRocket is designed to predict things like altitude, velocity, and trajectory. But for active control, you need a lot more. You need to be able to simulate the forces that the fins are creating and create a full 6 degree of motion model. We also need to make a simulation that lets us accurately represent our control system and our control architecture, including things like dynamic pressure, and gain scheduling, and a bunch of things we'll talk about in the next slide. For our flight simulation software, we decided to use Simulink, and Simulink is a graphical simulation environment built into MATLAB that allows you to model complex physical models using these blocks, kind of like Scratch. Instead of solving every differential equation and every equation manually, Simulink, each Simulink block represents a part of the system that Simulink calculates over time. For a simulation, we separated the model into 2 main sections, the flight computer and the rocket plant. The flight computer is everything on the inside of the rocket software, like the IMUs and the guidance code. And the rocket plant is basically everything that you would find in OpenRocket, like the aerodynamics and such. I won't be covering the flight computer much today, as I'm more on the mechanical side, but I will be covering the rocket plant, which is basically a virtual representation of the physical rocket. It's very similar to OpenRocket because it has everything, including the aerodynamics, the environment, thrust and gravity, but some things that we added were the servos and some custom aerodynamic models. In the simulation, we treat the rocket like a rigid body. So each component has its own forces and moments, and most calculations are calculated in the rocket's body coordinate system. And if you wanted to have forces such as gravity, which are in the Earth coordinate system, you have to have special vector transformations. So the most difficult part about creating the simulation are the aerodynamics. The aerodynamics of a rocket are broken down into individual components. So for all of you that have used OpenRocket before, it's basically the exact same thing. You know, you have the nose cone, you have the body tubes, the fins, the boat tail, and each component contributes its own aerodynamic forces, which are then combined to compute the total aerodynamic forces on the rocket. The 2 main forces that we're concerned about here are drag and normal force. Each component has drag, which acts axially, and also each component also has a normal force, which acts perpendicularly to the rocket and to the airflow. This becomes important when the rocket has some sort of angle of attack, because then these forces act in different locations along the vehicle and they generate moments. To calculate these forces, most programs use some variation of the Barrowman equations. These Barrowman equations were developed by an engineer at NASA, James Barrowman, over 50 years ago, and they're used to calculate aerodynamic forces on small-sounding rockets. These equations provide a relatively simple analytical methods for computing the rocket's center of pressure based on its geometry. And in our Simulink model, we follow a very similar component-based approach where each aerodynamic component, as you can see on the right side, is modeled individually and its forces are added together. These are calculated based on things like Mach number, angle of attack, atmospheric conditions, the vehicle geometry, and then these are summed together in the rigid body dynamics model. It's important to remember, though, that Barrowman equation is still just an approximation. I was talking to another team here yesterday, and their Barrowman equations were off by a factor of 10. So it really depends on the geometry of your rocket and what Barrowman can capture for you. Yep. So, like we said before, each aerodynamic component on the rocket has a drag force and a lift force. Drag acts opposite in direction of motion, and it's calculated using 1/2 p or rho times velocity squared, and this is called dynamic pressure. Basically what dynamic pressure is how much air and how hard is the air pushing against the rocket. The second major, and then also there's a drag coefficient and the reference area. For our simulation, we based our coefficient of drag on OpenRocket, and OpenRocket uses the same reference area for all components on the rocket, being the body diameter. The second force is the normal force, which acts perpendicular to the airfoil. It's very similar to drag force in the way it's calculated. It still has a coefficient, except the coefficient isn't the drag coefficient, it is the normal force coefficient. And that can be found using the normal force coefficient derivative. Basically what the normal force coefficient derivative is it's calculated in whatever software you're using based on the Mach number and angle of attack and the geometry of your part. In our simulation, we get this straight from OpenRocket. OpenRocket has a great feature called component analysis, and from there you can extract all of the coefficient derivatives for all your components and plug them straight into your Simulink simulation. This value isn't constant for every situation. It depends on the geometry, and it depends on the geometry. In our simulation, we calculate all of the normal force coefficient derivatives and use those to calculate the normal force on that part by multiplying it by the angle of attack. Yep, so here's just a quick Simulink model of how we model our fins. It has the normal force, and the drag force in there. And these basically are the same things, right? That is the normal force equation, and this is our Simulink representation. Okay. So once the Barrowman aerodynamics are modeled, this is where it becomes important for roll control, is using those Barrowman equations to determine the size of your fins. The goal is usually to make the fins large enough to require a high enough stability, but for roll control, a larger fin area also increases your normal force coefficient derivative, which means the fin generates more control authority than what your rocket really needs. So bringing this all together, when sizing the fins, we should look at how quickly the simulated rocket responds to the roll angle. And on the left is a kind of what happens when you have a big fin. There's a lot of oscillations, and this is because of sensor delay and backlash, sensor delay and backlash mostly. And we want a fin that gives a fast and well-dampened response while keeping the required fin angle low. Anything more than 5 or 6 degrees and your fins are probably a little bit too small. Anything, like for our fins, we have drag separation at about 7 or 8 degrees, but this can depend on all sorts of fin geometry. So that's the aerodynamics portion. Now we're going to be talking about the controls. Controlling a rocket is difficult because the system's constantly changing throughout the flight. Unlike a simple mechanical system, a rocket is highly nonlinear, meaning the relationship between a fin's torque and the fin command is not always constant or proportional. One of the biggest reasons that control authority changes throughout the flight is because of the aerodynamic force on the fins. It highly depends on dynamic pressure, so your control system will need to have different values at a low Mach number compared to a high Mach number. The aerodynamics themselves are also very hard to difficult because Bareman equations and other analytical methods or approximations, especially like in the transonic region or at larger angles of attack. Because of all this, a single PID controller with fixed variable gains is not enough. A controller tuned for one operating condition may become too weak or too aggressive depending on what Mach number you're traveling at. And this means we require some more advanced approaches. So Arbalest Rocketry uses a cascade controller, which is basically two PID controllers working together. It uses two control loops instead of one. And for our roll control system, the outer loop controls the roll angle, while the inner loop controls the roll rate. And this is because if you look at how a PID controller would work, you would need a set. The outer controller looks at the difference between the commanded roll angle, and the inner one controls at the actual roll angle. So it's like the outer, this is a simplified view. This structure is useful because the fins do not directly control roll angle. Fin deflection creates like an aerodynamic moment force, which creates a roll moment. That moment produces angular acceleration, and which integrates into roll rate, not roll rate directly. There's multiple layers of dynamics, so you can't get away with one layer of a PID. A cascade controller separates a single PID commanding roll rate can therefore be difficult to tune because it creates fast motion while also dampening that motion as the rocket approaches the set point. A cascade controller separates those jobs, so the inner loop controls the roll rate, and it's basically saying what roll rate do I need to get the rocket to a 0-degree angle, and the outer loop basically says, okay, command what roll rate that I need to get to that angle. And the last technique that Arbalest Rocketry uses is gain scheduling. And what gain scheduling is it changes the values of your controller throughout the flight and throughout wherever the conditions change. We tune our gain scheduling to dynamic pressure, and because control authority is strongly related to it. At low dynamic pressure, the fins generate relatively little force, so the controller needs to command more aggressively. And at high dynamic pressure, the fin deflection produces much more force, so the controller must be reduced to avoid overshoot or oscillation. This is also used to tune the controller around one reference condition rather than tuning it through all the different points in flight. Okay, so that wraps up the control section. Now we're going to be talking about the rockets that we flew this year. We had 9 flights with 2 successful roll control attempts. This is the Blue Jay series. Blue Jay Mark 2 is on the left, and Blue Jay Mark 3 is on the right. Each iteration we improved on a certain part of our rocket. So Blue Jay Mark 2. Blue Jay Mark 2 was not a success at all. The servo motors had way too much play. The rocket did not even fly straight. The stability wasn't great. The camera didn't work. And to improve on this, we created Blue Jay Mark II, again V2, and in this case, the servo motors, they still had too much play. There was bad phenomenon. We at least got some footage, and we got really good state estimation data. So our electronics lead was able to tune his state estimator, and we got really useful data. Our third rocket, Blue Jay Mark 2.5, is really where we were able to start getting things rolling. We were able to get working roll control. The first launch, we flew, and the gains were not tuned. The rocket did control itself, but it was overshooting like crazy. So what we did is that week, we took the data from the rocket, from the overshooting, we modified our simulation, we changed the values of the aerodynamics, and we flew again next week, and then we were able to get active roll control working. We flew it again twice just to get that video footage, and it was a complete success. For this flight, we did not use the cascade, or we did not use the gain scheduling, and we did not use the cascade controller. However, we just wanted to set the roll rate to 0, so our single PID was useful. And then our last Blue Jay rocket in the series was Blue Jay Mark III. Blue Jay Mark III was our L-class rocket that we needed to fly in order to get the DTAG exemption to fly Red Robin this year, which is our O-class rocket that we were flying. We had 3 launches of this flight. However, the first launch, we did not have really good hardware in the loop testing, and as the rocket went up, the roll control was reversed. So the rocket kind of did anti-roll control and spun out of control. The second and third launches were, we launched at a launch site with an 8-foot rail on an 8-foot rocket. It was super windy, and the rocket had tilt locked up. So we were unable to get the roll working on our big rocket. And yeah, all the video footage and all the data is available on our YouTube channel, including Canada's first roll control flight with video evidence, and also including all of our Blue Jay Mark attempts. Yeah, that concludes my presentation.
Thanks so much, Ronick and Arbalest. That is an ambitious project, and it is amazing to see your progress and what you've learned along the way. So thanks for sharing that. We're going to take another break, and we'll be back at 3 o'clock for a safety presentation about drone footage, and then the results of our raffle. So we'll see you all at 3 o'clock. we do here. So we're going to break until, let's see, 3:30, and then we're going to do the results of the raffle and some closing announcements. Awesome. All right, how about I just a few housekeeping items and then you take over? Okay, teams. Teams over in the arena, please come to the conference area for our raffle and a few final announcements. All right, let's get started. So we've reached the end of our conference. Thanks to everyone for being such a great audience and participating. A few final housekeeping items. So first of all, to the teams, please take down your tables and put away your chairs so that we leave the arena as we found it. Also, don't forget, at 5:30 today, we're going to launch a whole pile of beautiful painted stomp rockets that have been made by our guests and participants today. So please join us for that at the Baseball Diamond to help us count down each launch. Also, teams, throughout the week, please keep sharing on your socials and don't forget to use the Launch the North hashtag. We have a remote member of the media team who is continuously reposting your photos and videos on the Launch Canada site. Her name is Beverly Bambury, and she's been doing a great job this weekend with sharing your coverage as well. So please keep doing that. Also, please share the Launch Canada 2026 YouTube live stream link with your friends, family, and fans. It is launchcanada.org/live, or you can also find the link on the Launch Canada website. If you want to be on the live stream throughout the week, then please just report to one of our 2 live stream stations. There's one at Solids and there's one at Advanced. You can't miss them. And especially after you've just had a launch, it would be great to be interviewed by our live stream team and share how it all went. And thanks once again to our fabulous live stream team for doing such a great job with covering this conference. So with that, it is my pleasure to welcome back to the stage our conference director, Ariana Kresniak. She is going to announce the results of the first ever Launch Canada Conference raffle drive. Can we have a huge round of applause to Ariana?
Stay with me and cross off the items. Okay, hello everyone. Thank you very much for attending the talks and participating in this raffle. I hope everyone has their tickets ready. First, I need to give a big thank you to McMaster Rocketry for letting us use their nose cone to pull the raffle tickets. It felt quite on brand. So, the first prize is $50 in gift cards to Wendy's. We have a white ticket. It is numbered 14824-108. And I should say, if your number is called, go to the merch desk to be able to pick your ticket or get your prize. The next ticket, another $50 to Wendy's, is 253-11032. That is a blue ticket. The next prize, $50 in gift cards to Montana's. Go get yourself some ribs. It is a white ticket, 14824-144. The next is $50 in gift cards to Casey's Bar and Grill. That is a blue ticket, 253-112 225. Next. Okay, the next is $50 to Lot 88, the Steakhouse. Go treat yourself. It is a blue ticket, 253-11041. Next. The next, we have 8 bottles of hot sauce, homegrown by a Timmins business, JR's Hot Sauce. He grows it in his backyard in an assortment of flavors. It is a white ticket, 14824-177. Hey! So again, that's 14824-177. The next, if you were all really wanting to win that, don't worry. There's 3 more of it. So the next prize is, again, 8 bottles of hot sauce. 253-11158. A blue ticket. 253-11158. And another one. Oh, okay, we have to redraw because a volunteer had that ticket by mistake. So it's 253-11343. It is a blue ticket. 253-11343. Okay, more hot sauce? More hot sauce, 2 more. A white ticket. 14824-069. That's, hey! The lucky winner! And the last hot sauce draw is 253-11033, a blue ticket. 253-11033. Now we have $50 to Boston Pizza. They really like you, by the way. They say you're very polite and friendly and wonderful. It was nothing to get them to give us money. I just said we're from Launch Canada. They said, oh, I'll give you more. 253-11378, a blue ticket. 253-11378. More Boston Pizza? More Boston Pizza. 253-11212, a blue ticket. 253-11212. Woo! Okay. Oh, now we're getting serious. A Crimson Fury model rocket with 2 F motors, the launch rail, and the launch box. Batteries not included, sold separately. It is a blue ticket, 253-11134. Oh, okay, we got to recall that one. In my diligence to give out tickets, I accidentally gave to volunteers, but thank you for your honesty. White ticket, 14824-129. Wow! But don't remiss, there's a second one. So the other Crimson Fury goes to white ticket, 14824-067. Woo! Okay. Now, many of you have noticed the CAR booth here, the Canadian Association of Rocketry. They will issue your level 1 test, but you need to fly a rocket to go with that. So we have an L1 kit available to you. It is a blue ticket, 253-11289. That's 253-11289. Hey! So go to the merch table. Go to the merch table. Woo! Get that L1. Keep going. Get your L2. Okay. Now we're ready for Lego. Okay, and now it's the time you've all been waiting for. We are moving into the Lego set. That's the Lego Artemis NASA launch set. There's 2 of them again, and it's a white ticket, 14824-070. Woo! Okay. And these Lego kits have been staring me in the face as they've sat in my apartment for 3 months, desperately wanting to be built, but I can't. So one of you lucky ones will at 25311 255. A blue ticket. 25311 255. You won? Go to the merch desk, please, to complete your prize. Thank you very much, everyone, for attending this raffle, for attending all the talks. It was greatly appreciated and greatly enjoyed. That concludes our Launch Canada conference weekend. We hope to see you out on the launch range. Now, you don't have to go home, but you can't stay here. So we ask you to please clean up your tables, clean up your chairs, set them tidily against the wall, and just have a great launch week. Okay, now we need to collect all these tickets.